Hey programmers, welcome to our course on dynamic programming. If you're preparing for data structure and algorithm interviews and want to finally master this difficult topic, then you're in the right place. If we haven't met before, hey, I'm Alvin. I'm an ex-Google software engineer, and for the last decade, I've taught thousands of engineers how to ace their interviews and land their dream job. In the next 3 hours, I'll teach you how to solve dynamic programming problems from the ground up. You don't need to know anything about dynamic programming to get started. In this course, we'll start at the absolute basics and slowly work our way up to solving medium and hard problems. These will be the same types of problems that you could see on your tech interviews. For each problem, we'll take a two-step approach to learning. First, we'll head to the whiteboard. Visualizing algorithms is really key to understanding them. So this is where we'll break things down visually and come up with a plan. Then we'll head into my editor where we'll implement the code and run some test cases. I'll be coding in Python, but you can follow along in your favorite programming language. All right, I'm super excited to teach you everything you need to know about dynamic programming for tech interviews. So without any further delay, let's jump in. So in this course, we're going to learn how to solve dynamic programming problems. The first thing you want to know is there are really two main strategies that you can use to solve a dynamic programming problem. The first strategy is called memoization, and the other strategy is called tabulation. The main difference is the first strategy, memoization, is a recursive strategy. In other words, you're going to do things like write a function that calls itself, and of course, include a base case. Whereas for your tabulation strategy, that one is going to be iterative, so it operates using only loops. So at a high level, memoization is like the recursive flavor of dynamic programming, and tabulation is the iterative flavor of dynamic programming. A more practical difference when it comes to solving these kind of problems in interviews is a memoization actually uses a brute force solution as the baseline. And then from there, you optimize it using memoization. However, for your tabulation strategy, there actually is no baseline implementation. You really have to solve the entire optimized problem out the gate using tabulation. An important thing to know is that both memoization and tabulation will actually give the same big O complexity when it comes to their optimized solutions. There's an argument that tabulation is faster because there's no recursive overhead. However, they both end up giving the same big O time complexity, which is really what you care about on your tech interviews. The main thing we want to decide is, which one do we want to learn? Do we want to solve our dynamic programming problems using memoization, or do we want to learn tabulation? I'll tell you what you should definitely not do. You should not learn both of these strategies. Where most people go wrong learning dynamic programming is that they actually try to learn both of these strategies, which I think is a huge mistake. They actually have very different mechanics, and so learning one doesn't necessarily help the other. It's better to just focus on one. Focusing on everything is focusing on nothing, they say. I actually am a big advocate for learning memoization. Although most people are kind of scared of the recursive nature of memoization, you definitely need to learn recursion for your tech interviews, and memoization, to me, is much easier to apply to a wide range of problems. Mainly coming from the fact that with memoization, you can start with the brute force solution as a baseline, and then only modify it slightly to get the optimized solution. When I had my interviews at Google, I actually solved all of my DP problems using memoization, and I think you'll have success with it as well. You'll see that once you learn memoization, it's really like a recipe that you can apply to problems again and again, especially when it matters most on a technical interview. In my opinion, tabulation is harder to apply. And since they both have the same big O complexity, we're going to opt for the one that gives us more of a range when it comes to our technical interviews. So that's why we're going to learn memoization in this course. All right, so with that introduction out of the way, let's transition to our first problem. We're going to work on the classic Fibonacci problem. You probably already know how to solve Fibonacci using some simple code. However, the exercise here is going to be to solve it using recursion as well as memoization, because it serves as a great starting point as we learn this dynamic programming technique.
Hey programmers, Alvin here. Right now I want to work through this fib problem. Of course, we're referring to the classic Fibonacci sequence. This is a really important, computer science problem, and to me it serves as the foundation to really unlocking a few harder concepts down the line. So even if you've done this fib problem before, it helps to review it together right now. We're going to see this core pattern show up a lot during the course together. And so let's start by understanding what we should do in this problem. Well, we know that the Fibonacci sequence has a few certain seed values. We say that the first number of the sequence is 0, and the second number of the sequence is 1. And then to generate further numbers of the sequence, we just take the sum of the previous two. In other words, I can take 0 plus 1, and that gives me the next number, 1, right? So the sequence starts 0, 1, 1. Then from there, I continue this pattern, right? I can take the 1 plus 1, that gives me 2. I can take the 1 plus 2, and of course that gives me 3, and so on, so forth. And of course, I can generate the sequence of infinite length in this way. And so overall, in this rendition of Fibonacci, what we want to do is actually return the number at the specified index of the sequence, right? And so a really key insight about the Fibonacci sequence is to generate any particular number of the sequence, we must know some other numbers of the sequence, right? I can get 8 by just doing the previous 3 plus 5. If I wanted to actually formalize this problem a little bit better, what I'll have to do is understand that these numbers I have listed are really the elements of the sequence. And of course, I can assign some indices to those elements. So up top, I'll just label these increasing by 1, of course, but starting at 0. So I can say something like, hey, the 0th number of the sequence is 0, and the first number of the sequence is 1, and also the second number of the sequence is 1, and so on and so forth. So kind of jumping ahead a little bit. If I look at this particular position, what I see is, all right, it seems to be that the 7th number of the Fibonacci sequence is exactly 13. That's going to be overall the shape of this problem. All right, so how can we go about solving this one? And so for this particular approach, what I want us to do is actually work through this one recursively. I think the iterative solution is pretty straightforward, but I'm going to force us to solve this one recursively because it's going to help us learn some new topics along the way. So we'll kind of stick to a recursive mindset, and if you hate recursion, too bad, you'll learn to love it right now. And so looking at a particular example, let's say I wanted to figure out how I can come up with a solution for fib of 6. In other words, the 6th Fibonacci number is exactly 8. And so what I can start to do is figure out how to break down this problem. I know in general, to generate the 6th number of the sequence, I can take the 5th number and add that to the 4th number, right? It's exactly the rule of the Fibonacci sequence. Let me try to visualize this one a little bit better. So I'll represent the problem, fib of 6, using somewhat of a tree. And I'll represent an instance of the problem as a node of this tree. So I have my top level problem of 6. That'll be the root of this tree. And this is a really important way to actually visualize recursion because it really shows us how we're going to utilize our return values and reconstruct our final answer. So if this is a new pattern for you, don't worry, we'll walk through it pretty slowly together. And so now that I have this root of 6, I have to figure out how do I break down this problem. Well, like we just said, to solve fib of 6, what I need to do is break that down into fib of 5. So that'll appear as a child of that 6 node. In the same way, fib of 4 also needs to be solved to solve our main problem over here. And notice how I have these, children nodes, of course, below the fib of 6, right? As I go downward in this tree, I should be getting smaller and smaller numbers in blue, right? That would represent a smaller problem. Because I know once I have a small enough input in blue, then I would have somewhat of a base case, kind of inherent to the Fibonacci sequence. So let's take a closer look at this 5 node over here, right? This node represents the problem of fib of 5, right? What is the 5th number of the sequence? And I know in general, my pattern is, all right, if I want to calculate fib of n, then I take the sum of n minus 1 and n minus 2. So I'm just going to apply that pattern to this 5 node. In other words, on 5's left, it's going to have a node of 4, and on 5's right, it's going to have a node of 3, right? Doing a minus 1 and minus 2 respectively. And it's a similar trend for the 4 node on the right-hand side over here, right? It's going to have 2 children, of course, doing minus 1 on the left and minus 2 on the right, giving 3 and 2 respectively. So let's keep applying this pattern. What we're going to do is fill out the next level of the tree until we can't fill it out anymore. What we have to notice here is when it comes to actually building the full tree, we have to stop at certain nodes. In other words, once I have an instance like 0 as my input to this little subproblem, I can't actually shrink that problem size any further. So I'll highlight all of these nodes whose input is 0, right? That represents the 0th number of the Fibonacci sequence. And something inherent in the problem is I can't really break that problem down any further. I know that for those particular nodes, they ought to return 0. Right? Because the 0 number of the Fibonacci sequence is exactly 0. So in green, I'm going to represent the result or the answer to those subproblems, right? I'm going to put their answers above the problem itself. Right? So I'm trying to be very, very particular in my drawing. I'm always going to write a return value above a node here. And I have a similar case for all of my nodes who have an input of 1. Those are also a base case, right? Because the first number of the Fibonacci sequence is exactly 1. So we'll also fill in those 1s above. Cool. Now that I have some floating return values, I can start to reconstruct my larger problems at hand. So let's stay focused on the left-hand side of my tree. Let's look at this particular node. So I'm looking at this node of 2, and I have a left-hand value and a right-hand value ready to compute. I know that if I look at this node of 2, it's trying to figure out what's the second number of the Fibonacci sequence. And so at this node of 2 in blue, what I can do is just take the sum of its children, right, of those green values. So 1 plus 0 gives me 1. And if I do a quick sanity check, that must mean that the second number of the Fibonacci sequence is exactly 1. And this pattern continues up the tree, right? At this node of 3, I take the sum of the 1 plus 1, and I get 2. If I do a quick sanity check, that must mean the third number of the Fibonacci sequence is 2. What we're doing right now is really stepping through how a recursive code would actually return, right? Return means return to your caller, right? So return to your parent node. And so we'll fill in the rest of the values over here. And bear in mind, as you kind of draw out these diagrams, maybe for yourself, hopefully on pen and paper, or even on a whiteboard, it's really important, at least for me, that you check for correctness as you build the tree. So if you're in an interview, it really helps to not just check for your top level answer being correct, but at any points of your trace, you should have logical information. In other words, by just looking at this node, right, I have a blue node of 3 over here, whose return value is 2, that logically implies that the third Fibonacci number is 2. And that's totally correct, so I'm good to go for now, right? It would really be a drag if I kind of sketched through this entire drawing, only to realize I had a little typo or miscalculation somewhere below in the tree. So I highly recommend that you stay very aware of your subresults as you kind of trace through a diagram like this. So let's continue to build up these subsolutions. So I know that this node of 2 is going to take the sum of 1 plus 0. That gives me 1. Then finally, at the parent of 4, it's also going to take the sum. So 2 plus 1 is 3. And that must mean that the fourth Fibonacci number is, of course, 3. So let's speed this up a little bit for every other node in the tree. So we're going to add all these up, so on and so forth. Now at the tippy top, we see that this node of 6 at the root is going to take the sum of 5 and 3. And of course, that gives me 8, which is exactly the punchline, right? The sixth Fibonacci number is indeed 8. And so looking at this pretty large tree, you might realize that, hey, our top level problem was asking for the sixth Fibonacci number, not a very large number in the sequence. However, we had to use a lot of nodes to actually represent that problem, how we broke it down. And that's something really important about this Fibonacci sequence, right? It has a pretty interesting complexity, a pretty large one at that. So let's try to analyze the complexity of this. We know that every node of this visual tree represents a recursive call, right? And so the number of recursive calls I make over here, or the number of nodes of the tree, should roughly represent the time complexity of this solution. You're probably already recognizing that it's going to be a very, very large one. Let's go step by step over here. And so to analyze the complexity of recursion like this, I think it's really important to notice any patterns in the tree. To me, it's all about looking in the tree, right? I can kind of figure out at least the ballpark of the time complexity without even writing the code, right? Just using this visual. And so at first glance, you might notice that this one is pretty hard to analyze because the tree is asymmetric. In other words, notice that it's a little taller or deeper on the left-hand side, then toward the right-hand side of the tree, it's actually much more shallow. And that kind of asymmetry makes us feel a little uncomfortable when it comes to figuring out any patterns. So here's what we'll do. Let's actually try to analyze this one by drawing an analogy. So let's ignore this exact Fibonacci tree right now and go for a more symmetric example. So let's say I had a similar recursive code that had a more symmetric recursion. So let's say I had some top level call with a value of 4. And let's say that this top level call to 4 actually made 2 more recursive calls, but both on a -1. In other words, the left child is the same as the right child, which is different from our classic Fibonacci, right? Fibonacci, our left was -1 and our right was -2. But now I'm just doing -1 on both sides. If I continue that pattern, that should give me a nice symmetric tree. Now let's say I had some base case roughly when my value is 1, so I can stop building the tree from here. And so this has a nice symmetry to it. Let's try to notice any patterns now. If I look at the different levels of this tree, let me look at how many nodes there are across a level. So for example, my very, very top level, and there's one node on that level. On the next level, there's 2 nodes, and then 4 nodes, and then 8 nodes. And you can probably see how this pattern scales, right? If I drew more of this tree, let's say I had a farther base case, it would be 16 nodes, and then 32 nodes, and so on. And so you probably realize the obvious pattern here, right? At the very top, at the root of my recursive tree, I have one node or one call, and then from one level to the next, I double it. I multiply by 2, right? And I do this process basically for every level of this tree. So that begs the question, how many levels are there in this tree? Well, just looking at this kind of particular concrete example, there's definitely about 4 levels, right? And I can kind of understand how to designate each level by just looking along this left-hand path, right? So colored in yellow, notice that I have 4, 3, 2, 1. That's just a decreasing pattern. So when it comes to the number of levels, it's pretty obvious to me that it's exactly n levels, right? If my top level problem at the root is where n equals 4, then I have, 4 levels, or in general, n levels. So it's pretty clear to me that when it comes to figuring out the total number of nodes in this tree, which implies the total number of recursive calls we make for this kind of toy problem, it looks like I would multiply 2 by itself n times over, which is a definition of an exponential 2 to the nth power. Cool. So maybe you're a little bit skeptical, and here's where we can either, really buy into kind of the big O complexity, or we can get bogged down by the finer details. Something that you might fall into sometimes, but you have to kind of be very aware of it, is big O is really just an estimate. So if you actually plugged in some values here, you might notice, all right, if I did 2 to the 4th power, right, because 4 is my n in this particular example, that would be 16. And so if we actually counted the quantity of nodes in this visual tree, it would not be exactly 16. I'll label them over here starting at 1. There's actually going to be 15 nodes. So it's off a little bit. But if we, understand big O complexity, we know that if we have something that's of the shape of like 2 to the n minus 1, we can ignore the minus 1. And what's more is, even if it was off by like 5, right? If it's a minus 5, that's still a constant that we're subtracting. That still is dropped from the big O notation. So overall, I would consider this particular example as having O of the 2 to the n runtime, which would be exponential, pretty slow, right? So while we're here, looking at this symmetric example before we hop back into Fib, let's try to recognize what the space complexity is. We know that the space complexity for recursive code is going to be more or less the number of stack frames that we use, right, for our recursion. Because whenever we make a recursive call, that information has to be stored on the call stack, right? As we kind of make different function calls and also return from function calls. And so this is actually something I notice students have quite a difficult time analyzing. And so what I'm going to do is really trace through how we would make these recursive calls, as well as how to visualize the call stack, right? So this top level call of 4 would be added to the stack, right? So stack will be just a little rectangular block, right? And then as I make recursive calls, let's say now I call upon 3 as my input, that's also added to the stack. Notice that it's added on top of the 4, right? And really what we have to recognize here is every time we make a call, we're adding a new stack frame, and we only get to remove something from the call stack when it returns. So far, none of my calls have returned, right? Until I have 1 at the top of my stack, right? At this point, I've kind of bottomed out at like a base case, so I can return from that call, which also means I remove it from the stack. At this point, I need to evaluate 2's right child, so I make another call to 1. And this process continues, right? Now I'm done with both of 2's calls, so it can return. Now I'm back at 3, but 3 has to call upon its right. And the same thing happens. What you'll notice at this point is, although there are many different stack frames we would have to eventually push onto the call stack, at any point in time, there's only about 4 different stack frames on the call stack, right? It's not as if that we store like all of these different stack frames simultaneously, right? It doesn't really make any sense. To add certain stack frames, you must have returned from other ones. So it's actually the case that the space complexity due to the call stack would just be O of n. Overall, we're looking at an exponential runtime and a linear space complexity. All right, so for this particular symmetric example, it has an exponential runtime and a linear space complexity, but how about for our actual Fibonacci tree? We know our Fibonacci tree is more lopsided. It's roughly going to be like half the size of that, and you can take my word for it, it would actually be the same big O complexity, right? Still 2 to the n, and then just an O of n space complexity. And so, kind of taking a lay of the land over here, the space complexity seems reasonable, right? However, whenever we have an exponential, usually that's not good enough. And there is actually a better or faster way to solve this one recursively, which is what I want to expose us to right now. So let's go back to the recursion tree for our fib problem, right? And so what we can do is try to recognize any patterns within this tree. Do you notice any duplicate work, right? And this is all about understanding, what this diagram represents, right? Every node I have drawn in here with its corresponding number represents a problem. And you can see I have many duplicate problems. So for example, if I look at this subtree, that subtree represents a subproblem, right? Rooted in 4. So I'm asking for the 4th Fibonacci number. Not only do I need to calculate that on the left-hand side of the tree, but at some other point down the line on the right-hand side, I need to calculate that same exact subproblem, right? These two subtrees are identical, and they both represent the same problem, the 4th Fibonacci number. And this pattern actually applies recursively because this strategy is recursive, right? So you can notice probably some other different duplicate subproblems, right? If I root myself at 3, I have to calculate this subtree 3 different times, right? And notice that that 3 subtree is also internal to the fib of 4, so it's really duplicate. And there are a few other duplicate subtrees you can recognize over here. So we have a lot of duplicate work in this kind of brute force recursion. And if we actually store some subresults, then we can forego having to recalculate any of these subtrees down the line. And so really what we're looking to do is kind of prune out some branches of this tree to avoid some duplication. So what I'm going to do is kind of ignore this right-hand tree of 4. I'm going to take that out because I would have calculated it on the left-hand side somewhere. And I'll do the same thing for this kind of middle tree of 3. So I can ignore that as well. Cool. Likewise for this 2. And so at this point, we don't really have any full duplicate subtrees, right? I kind of took them out of my drawing. So if we actually store some results as we calculate these subproblems, this really represents all of the recursive calls that we'll have to make, right? And so you're wondering, how can I actually implement, that kind of pattern in my code? Well, it's all about just storing some additional information. So let's step through still fib of 6. So I want the 6th Fibonacci number. In the long run, we should get 8. And the strategy I'm introducing right now is called memoization. And so when it comes to implementing memoization in your language of choice, it's all about storing some additional data in a memo. And your memo is typically going to be your hashed data structure. So it could be like a hash map or a dictionary or object, depending on your weapon of choice here. Right? It's really important that I choose some data structure that gives me an O of 1 lookup time, right? So usually that would be your hashed data structures, whatever that is in your particular language. And so let's step through this one again, but now we're going to store some data inside of our memo. And so we have the same base cases as before, right? We know that the first Fibonacci number is 1 and the 0th Fibonacci number is 0. And when these values return to the parent of 2, we're still going to calculate the sum over here. So 1 plus 0 is just 1. But now that I have this result, I can store it in the memo. So I'm going to make the key represent the input to that node or that recursive call. And then its value is going to be that return value. And so if I look inside of my memo, it's a reminder that the second Fibonacci number is 1. So we'll continue this process. I know that I have a base case over here. It's still the case that the first Fibonacci number is 1. And I return to the parent. I calculate that, hey, the third Fibonacci number is 2. And I'm going to store that in my memo as well. And here's where things get a little more interesting. If I look at this node of 2 over here, I've actually calculated this subproblem before, right? I can check that by just looking inside of my memo. My memo says, hey, the second Fibonacci number is 1, so without having to recurse and build the full subtree once again, I'll just go ahead and fetch the stored value in my memo. So I'm just going to jot down a 1 above this node of 2. And I can return to my parent, and I figure out that, hey, the fourth Fibonacci number is 3. And of course, I want to be sure to return that, but also store it in my memo for the future. And same thing happens at this 3 node, right? This 3 node is, again, in my memo. So without, recursing through my tree, I'm going to just fetch that value from my memo. Right? I already know that, hey, the third Fibonacci number is 2. And so I can calculate the value at my parent, right? Fifth Fibonacci number is 5. Be sure to store that in your memo, and so on and so forth. By the time we get to the very top of our tree, of course, we have the fact that the sixth Fibonacci number is indeed 8. And I avoided a lot of the duplicate recursive calls. So it's clear to me that we avoid a lot of duplicate work, but what exactly is the runtime now, right? And so we'll try to notice some patterns. So this visual tree represents our Fibonacci recursion after we implement this memoization strategy, right? I'll try to generalize it over here. So I'll kind of tidy up these edges over here. And let's say I increased the size of this problem. So instead of fib of 6, what if I asked you for fib of 7? That recursion tree would look something like this, right? Notice that the root is now 7, of course. And it's still the case that the left child is -1, so a 6, and the right child of the 7 is a -2, or a 5, right? Still obeying the rules of Fibonacci. And I only added 2 more nodes. If I increase the problem size to fib of 8, I would still add 2 more nodes. So every time I increase my input by 1, I only add 2 nodes. It's always adding a constant number of nodes. At this point, our problem scales linearly, right? In general, we're going to notice that we have basically 2 times n nodes. And notice that it's not 2 to the n, right? I'm saying 2 times n. And so we can simplify that to a runtime of O of n. And the space complexity is still the same, right? Notice that the space complexity for this algorithm is really just going to be the height of the visual tree. It still looks like a linear chain, right? If I go along the left-hand path, it just goes 8, 7, 6, 5, 4, and so on. So definitely an O of n space complexity.
All right, so now that we have a good idea about the plan we want to use, it's time to code it up. In the next section, I'm going to hop into my text editor where we can implement the code and run some test cases. It's really important that you follow along. If you head to the video description, you'll find timestamps along with links to the coding workspace that I'm going to be using. So feel free to code along there. Or if you're more comfortable, feel free to edit in your own text editor. I'll be sure to pull up test cases on the screen so you can also test your work. I'll be coding in Python, but in our workspace, you can feel free to switch the language to Java, C++, or JavaScript as well.
Hey programmers, Alvin here. Right now I want to go over a Python solution for this fib problem. So we'll jump right in. Let's start by laying down our base cases, right? So our base case, like we said in the approach, was if our input number n is 0, then return 0. If our input number is 1, then return 1. So that should just be a matter of some conditionals for us. So we'll check if n is equal to 0, then just return 0. And then also if n equals 1, then return 1. So nothing too fancy. And now in the recursive case, why don't I start by just laying down the brute force. So here I can calculate my answer by returning the sum of the previous 2 Fibonacci numbers. So fib of n minus 1 plus fib of n minus 2. And before we even try to implement the optimal solution, let's just go ahead and run this brute force. It's probably going to time out because we already spoke about how this has a 2 to the n or an exponential runtime. Should be able to pass at least some of the examples here. And I expect, that we time out on some of the larger inputs. So it looks like on test 6, we take a little bit too long. If I look at that test case 0, 6, it looks like even once we pass it along the 35th Fibonacci number, that's too large for our exponential solution to actually deal with. So now we'll work in that memoization strategy, right? And so to implement that, in Python, I want to make sure that we are able to pass a dictionary into this recursive call, and that way all of the recursive calls share that dictionary. And I'm choosing a dictionary in Python because it's basically how Python implements like a hash map structure, because it can give me an O of 1 lookup time. So the way I typically implement this is I want my main function to have the name that's going to be tested. So I need to make a function called fib. But for my actual recursive function, maybe I'll just rename that. You can call it like fib helper. Typically what I do is just put an underscore at the front of the name. And then for our main function, we'll still take in n. But what I want to do is really just delegate to my helper function. So I'm going to just return whatever my fib helper returns. But I want to pass along to it an empty dictionary. So I'll just give it a dictionary just like this. Now that's going to be a memo. So I can take that in now. And I want to make sure that this memo is passed along to all of the recursive calls over here as well. So right when I make these recursive calls on line 13, go ahead and pass along that same old memo. Cool. So now I'm able to share this single dictionary among all of the recursive calls when I call _fib, right? So that's looking pretty good. And now I need to add an additional base case, right? So recall from our approach video, we said that we need to be storing information inside of our memo. In particular, we want keys of the memo to be arguments n, and we want the associated values to just be the return values. So let's go ahead and check. If n is inside of the memo as a key, so if n in memo. So if you're unfamiliar with some Python syntax, this is just checking if n is a key in a dictionary. And if it is, then return the stored value associated with that key. Nice. And what I want to do is, now I need to put data into my memo, and that should just be about modifying line 16, right? And so this is a very canned formula. We're going to see this appear many times. I just take my old return value, and I replace the return with a line that stores that value into the memo, using n, or the argument to our function, as the key. Cool. And then once I do that, I just need to complete the same old return. So I'm just going to return memo square bracket n. So I'm still doing the same return. I'm still returning the same information, the same number. But before I return, I'm now storing that result, that number, into the memo. Because the whole point is, maybe later on in my recursion, I actually need to know that value, that return value for a given n. And so I have my memo checking logic, I have my memo storing logic, and I also, of course, passed along a new dictionary for my recursion. So with that change, let's go ahead and give it a shot now. I'll clear this out. Let's give it a run. We should be able to pass all of the test cases now. Yep, and there we have a nice solution for this fib problem. So I just want to go over a common misconception. So it's really important that for most of these like memoization problems we do together, you're going to notice that it's really, really easy to just modify a brute force solution with memoization after the fact, right? Because I just apply these three changes. That is, I add a base case to check if a key is inside of the memo. I'm sure to store information into my memo. And then of course, we need to pass along our memo to all of our recursive calls. Something that students kind of do when they kind of first learn memoization is they write very heavy-handed logic, and they kind of write bad patterns like this. So I'll say, I don't know, memo n-1 equals like this recursive call, and they write something very similar for n-2, right? So you want to avoid, code like this, right? Instead of writing like preemptive logic where you try to memoize your child calls, right? So if I picture this as a tree, like the parent would be fib of n, and the child or the children would be fib of n-1, fib of n-2, right? You don't want to write any memoization logic explicitly about the child calls. Instead, just write your logic for yourself. So my logic is simply about n, because I know when I just make the recursive call, it's going to be like self-service, right? Every call is going to store itself into the memo. That way I don't have to duplicate my code too much. So definitely give this problem a shot on your own. Once again, if you needed some help with this one, it's a really core pattern. We're going to utilize this memoization formula plenty of times throughout the course. Hey programmers, Alvin here. Right now I want to show you the approach for this Tribonacci problem. And so I know you're thinking, why is he having us do basically a ripoff of Fibonacci? Well, I think it's really important that if you want to get good at these algorithm things, then you have to have a certain level of repetition. As the saying goes, one is none, right? So even though, we've just done the Fibonacci problem, doesn't mean that it's completely something that we've mastered. So if anything, this should be a quick little review, right? Of course, I want you to solve this Tribonacci problem recursively. And so let's take a look at the sequence. So here is a few numbers of the Tribonacci sequence. What you'll notice is in this particular problem, like before, I want you to give me back a particular number of the sequence. So imagine that we had corresponding indices for each of these numbers. When it comes to the Tribonacci sequence, we're going to have 3 separate base cases, right? The 0th number of the sequence is 0, and also the first number of the sequence is 0, and the second number of the sequence is 1. So with those 3 seed values, we can come up with our general rule. Right? Just like before, to calculate a number of the sequence or the next number of the sequence, you just take the sum of the previous 3 numbers, right? Or in general, to calculate trib of n, you do the sum of n minus 1, n minus 2, and n minus 3, and there you'll have your final answer. Right? So kind of jumping at a particular spot within the sequence, if I took the sum of 4 plus 7 plus 13, that would give me exactly 24. So you should feel right at home in this particular problem. And so let's start to draw this one out. I don't want to skip any steps. And so before we start building this one, let's have some foresight and figure out how to visualize a problem like this, right? And what's great about visualizing it is that at least if we spend some time, sketching out, a structure of the problem, like visually, it can also help us figure out the complexity of this particular problem. So right now I want to step through calculating the 5th number of the sequence, which should be 4 in the long run. So like before, I'm going to represent an instance of this problem just with a tree. And so my top level problem will be the root of this tree, right? I want to find trib of 5. And I know that I have to break this problem down into 3 subproblems, right? In other words, I can generate 3 children by doing a -1, -2, and -3, respectively. And I'm just going to carry over that pattern for as many nodes as I can. And of course, whenever I hit like a base case, I can't break that node down any further. We know that when it comes to our Tribonacci problem, we have 3 separate base cases, right? Representing these particular return values. So I'm just going to plug in these subresults. So I should have all of these calculated values, right? 0th number is 0, first number is 0, and also the second number is 1. Now I can start reconstructing my sub-solutions, right? So if I take a look at the particular, to the left, the 3 node, I take the sum of its 3 children. 1 plus 0 gives me 1, right? So the third Fibonacci number is 1. And I'll just continue this pattern, right? Every parent node just takes the sum of its 3 children return values. So I get values that look like this. And finally at the root, I just take the sum of 2 plus 1 plus 1, which gives me a final answer of 4, right? Very similar to our classic fib problem. So this would be a working solution, basically just doing the same recursive code, except we're going to have 3 recursive calls, which makes sense because every call we make corresponds to a branch that we have in this visual tree. However, what's the complexity of this one? It's pretty slow for the same reasons our Fibonacci code was slow before, right? So if you take a look at this particular tree, I can derive the time complexity of it. Because I know that for my recursive code, the time complexity is at least going to be the number of recursive calls that I make. And if every recursive call corresponds to a node of this tree, I have to figure out what the long-term pattern for the number of nodes is in this recursion tree. So I know that the height of this tree is pretty obvious. It looks like it's going to be along the order of n. And how do I know that? Well, if you look along the left-hand path, it just goes 5, 4, 3, 2. And in general, that's roughly n things, right? Now I'll just think about how many nodes are across on every level. At the top level, there's 1 node. And to get to the next level, I multiply it by 3. And I continue this pattern, right? As the tree gets bigger and bigger, from one level to the next, I would continue by tripling the number of nodes, right? Very similar to our Fibonacci problem. And so you guessed it, the complexity of this is 3 to the n. So an exponential, but with a base of 3, right? And it is the case that our space complexity is a pretty reasonable O of n, right? Of course, we're referring to the space complexity due to the call stack, right? And in general, we can figure out the space complexity from the call stack if we draw out the tree, and we can just look at the height of the tree. The height of the tree being basically the number of levels. And there's roughly, 4 levels here, so I guess it's off by 1, even though our input was 5, right? And so to make this one a little faster, of course, we can just notice any duplicate subproblems, right? So same story like we're used to. Take a look at this subtree, rooted in 3, and I have this subtree appearing here as well. And so I want to avoid resolving that subproblem. We're going to use the same strategy as before, but this time I want to use a different word to describe it. Really what we're utilizing here is dynamic programming. So dynamic programming is really a type of problem solving where we utilize any overlapping subproblems, right? In other words, I have this subproblem of calculating the third Tribonacci number, and if I can store that information the first time I solve that problem, I can utilize it later on because I'm probably going to encounter that same subproblem, right? So this is in the family of dynamic programming strategies. And so far, we've been working with memoization. So really, memoization is just one way we can implement dynamic programming. And so if we use dynamic programming wisely, we should be able to forego that duplicate subtree, right? And overall, we'd be looking at an O of n runtime and O of n space complexity if we implemented that correctly, right? And so to implement that, of course, we're going to use some hash data structure to build that memo. So for my Python people, you're going to use like a dictionary. For my JavaScript people, you're going to use an object. For my Java people, going to use a hash map, right? Any fast lookup data structure. And at this point, we have a pretty optimal solution for this Tribonacci sequence, right? It should be able to run in a pretty decent time. And so with that, what I want you to do is give this code a shot on your own. But don't forget, if you get stuck, we do have a code walkthrough available as well. So give it a go. Hey programmers, Alvin here. Right now I want to go over a Python solution for this Tribonacci problem. So we'll jump right in, really just a spin-off of course, that fib problem. So I'll start with my base cases. I have 3 of them over here. So first base case, if I have n equal to 0, or n equal to 1, then in either case, the 0th and first Fibonacci numbers are both 0, right? My other base case is if n is 2, then the second Fibonacci number is just 1. And using those scenarios as my basis, what I can do is now have my recursive call. I can just return the sum of the previous 3 Fibonacci numbers, right? So I can call Tribonacci of n minus 1, and add that to n minus 2 and n minus 3, of course. So why don't we just run this code, test it out, and I should probably time out because we already know that this gives us an exponential 3 to the n complexity. And we'll probably need to memoize this one. Cool, yeah, looks like we fail example 07. If I look at that test case, the 7th example gives us an input of 37, which is fairly large, right? Especially given an exponential runtime. So let's go ahead and memoize this to see if we can pass that last example over there. And so you should be familiar with this pattern a little bit by now. So what I'll do is I'll be sure to maybe refactor this. I'll make this my helper function. So just really quick, I'll put an underscore in front of it. It's still a valid Python function name. And I want my main function to be called Tribonacci. Tribonacci takes an n. And all I want to do is really just invoke the helper function now. So I'll just return underscore Tribonacci and pass along the original argument n. But in addition to that, I need to pass along a nice new and empty memo dictionary. So there it is. And now I can take that in for my helper. So over here, I'll take in and pass along that memo dictionary. And again, I'm using a dictionary here in Python because it has a very fast lookup. It's a hashed data structure, so it's going to give me an O of 1 lookup time. And when you're in an interview, I think it's really important to actually mention and defend why you're choosing specific data structures, right? Show that you are knowledgeable about the material. So I'll start by adding an additional base case. So if my argument n is in the memo, that means that I've encountered like this subtree in the visual, or I've encountered this input before. So I just want to return the stored value in the memo. Cool. And in addition to that, now when I have my return line, I'll just take this expression, whatever it evaluates to, store that in my memo. So memo of n equals that thing, and then still complete the same old return. So I can just do that by keying into my dictionary using that same n as the key. So again, recall that our dictionary has keys that represent arguments to our recursive function, and the associated values are going to represent the return value for that argument. So with that change, let's give it a shot now. See how far we get. Nice. It looks like we're able to pass all of the examples in a reasonable runtime. Cool. So it's about the second or third time you've seen this kind of classic Fibonacci-like memoization strategy. We're probably going to increase the difficulty for the following problems, but it should really, really rely heavily on this core pattern, right? So typically when we kind of go through these memoization problems, we'll start with a brute force algorithm, typically recursive, and then it's just a matter of adding our nice memo logic, and you always make the same changes, right? Add your base case, add your logic to store data into your memo, and be sure to pass in a dictionary that is shared for all of your recursive calls, right? And so if you had any issues implementing this Tribonacci problem, I recommend that you try it again on your own. Really have some confidence in your ability to code this problem, because it will get more difficult in the next few sections. Hey programmers, Alvin here. Right now let's go over the approach for this sum possible problem. So in this problem we want to take in two arguments. We're going to be given a amount as well as an array filled with numbers. What we want to do is return true or false, indicating whether or not we can use some numbers of the array to generate the amount by adding them together. In this particular example, I should return true because I can totally make 5 by adding up some numbers in the array. There are a few different ways to do that. I could have done 2 plus 3, or 3 plus 1 plus 1, or also 2 plus 1 plus 2, and there are actually a whole bunch of other different ways you can sum up to 5. But since I have at least one way to generate 5, I'm going to return true. So overall, we're just looking for a Boolean return type for our function here. It could be the case that based on the inputs we're given, it might not be possible. So if I gave you a target amount of 15, and I gave you numbers to choose from, like 6, 4, and 10, that would actually be impossible. So you should return false. All right, so how do we start attacking this one? We'll step through an example where we want to generate a target amount of 4, and we have numbers 1, 2, and 3. This should be a sufficiently large example to step through. Here my intuition tells me that smaller amounts are easier to calculate than larger amounts. So what I can do is try to shrink my amount as much as possible until I get to a trivially small amount for which I know the answer for. So let's say I start with my amount of 4. What options do I have here? Well, if I think about my first choice, what I could do is take a 1. So this 1 is going to represent the first number I can choose, right? And what I can do from there is actually subtract that 1 from the 4. That would give me a new amount of 3. But still at the 4 node over there, what I can do is also maybe consider taking a 2. If I do 4 minus 2, then my next amount is 2. And the final option would be taking a 3. If I do 4 minus 3, that'd give me 1. And at this point, I'm starting to shrink my problem size. So inside of the nodes in blue, we're going to have listed the amount that we're trying to break down. And then the numbers in yellow on the edges represent the choice of numbers that we choose. And we're starting to shrink our problem size. So let's say we take a look at the 3 node on the left. We can break it down further, right, using my options of 1, 2, and 3. And that would yield 2, 1, and 0, respectively. If I take a look at this 2 node over here in the middle, I have to watch out because I can only use some of my numbers for valid moves, right? In other words, I can do 2 minus 1 or 2 minus 2, and that'll give me 1 and 0 respectively. But what I should not do is 2 minus 3, right? Although I have a third option of doing a 3, that would be too large right now, and that would actually bring me to a negative quantity. So we're going to need to watch out for that in our drawing, as well as when we implement the code. Similarly, for this right-hand node of 1, I can only subtract 1 for it, because using any of the other numbers would bring me to a negative quantity. So we'll continue this pattern for all of our nodes until we can't break them down any further. And this would be the complete tree. Really what we're describing is the decision tree for all of the options that we can possibly make. Right? So although I'm saying tree here, I'm really referring to the fact that we're breaking this problem down recursively. When we go ahead and implement this, we're not going to have to build any like tree data structure, but we're going to solve it using recursion, right? I use this tree as a way to actually understand all of the options I can take. So since we know that this tree visualizes the recursion, well, where can we locate the base case? Well, that would really be just the leaves of this tree. What we can do is recognize that we have a bunch of 0 nodes over here, and to me that would be a trivially small amount that I can always know the answer for. So that's going to be my base case, right? In other words, if someone gave me an amount of 0, I'm just going to return true. Why does that make sense? Well, I can always generate 0 by just taking no elements of the numbers array. And I can always return true regardless of what numbers you give me. You can even give me no numbers and that'd be totally fine. I can still generate 0 by taking none of those numbers. And so what I'll do is jot down this return value above all of my 0 nodes. Those are going to be my base cases, right? My base case calls. And I know that if I see a single true anywhere in the tree, then it should be possible to generate the amount. Obviously here we can't really go wrong, and we have a lot of different ways to generate the amount. If you look within this tree, not only do you know that there are a bunch of different ways to make our amount of 4, but you can actually see what numbers you added to generate that amount. For example, if I look at this path, this represents doing a 1 plus 2 plus 1 to generate 4, right? I'm just adding the numbers that I have along the edges here. So this tree tells you a lot of information, and you can use it to solve a bunch of different variations of this problem. So now let's start to look at how the values return here. So given a parent node, if it receives a true from any of its children, then it's also going to return true. So that would evaluate something like this. Until we get a true at the top as our final answer. So far we've described the brute force way to calculate the answer here, and I think it's worth going through the complexity. So here I have two arguments to my function. If we say that a is the amount and n is the length of numbers, we can say that the time complexity is going to be n to the a power. So this is going to be exponential. So what we're doing here is putting n in the base of the exponent because we know given a node, it's going to give at most n children because I have to branch for every option of number in the numbers array. And I'm putting a in the exponent because I know that the height of the tree is at worst going to be a. You can easily see that in this particular example. If you start at the root and just keep going to the left, it goes 4, 3, 2, 1, 0, which would mean that the height of the tree in the worst case is exactly a if I had to keep subtracting 1 from my node. So overall, I'm looking at an n to the a complexity, which is an exponential and typically going to be too large to actually run for reasonably large inputs. We talk about the space complexity, it's just going to be O of A right now based on the height of our tree, right? We know the height of the visual tree would give us the maximal stack depth. So how can we do better? Well, you should probably catch the drift by now. Take a look at this tree and notice if you see any duplicate work. What I can notice here is I have some duplicate subtrees, right? I can see these subtrees rooted in 2 that are identical, and I even have smaller subtrees that are the same, like the ones rooted in 1. And I know that if I have duplicate subtrees in this visual, that means I'm trying to solve duplicate problems, right? If someone asks me, is it possible to generate 2 for the first time? Then later on, if someone asks me again, I should have just memorized that answer, right? And so here we're going to use that memoization strategy. Just store some solutions in some cache. That way I can fetch them later on. If you implemented memoization like we've seen previously, then you would be able to trim out some branches of this tree, ending up with this smaller structure. What would this memoized complexity be? Well, we'll still say that a is the amount and n is the length of numbers. What we did was actually remove the exponential nature of this problem now. We'll say that the time complexity is O of a times n. So it's no longer an exponent, I'm simply multiplying them, right? So a still represents the number of levels within my tree, right? The height of the tree. And then n represents the width of my tree, right? For every level, I will have at most n nodes. And it would still be the case that our space complexity is O of A. We would still use A stack frames on our call stack due to the recursion. And in terms of storing our memo, we know that's also going to be linear in A. And when it comes to the hash map we use to store our memo, the space complexity for that is still going to be O of A, because we're just going to use every possible amount as a key of that memo. Before I let you go, let's step through an amount that would not be possible given some numbers. So we'll step through a scenario that should return false. So my amount is 15, and I have numbers of 4, 6, and 10. If we attack this one the same way, we'll start with 15 in the root, and we'll subtract each option of number, giving us 11, 9, and 5. And I'm going to carry this over as much as I can until I can't reduce my amount anymore. So the full tree will look like this. The nodes highlighted in red are the nodes that I can't break down any further because it would bring me to a negative quantity. So if I have any remaining quantities in those red nodes, then I know that would mean those quantities are not possible to be generated. So those should be a base case that return false. And now I can evaluate my returns in the same way as usual, right? I just bubble these up to their parents. A parent is going to return true only if one of its children calls also return true. But everyone here is false, so I'll get false all the way back up the tree. All right, programmers, I think that's all I got for this approach video. What you want to do is possibly give this one a shot on your own. See if you can translate our visual diagrams into some code. And then if you get stuck, you can find me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now, let's go over the Python solution for this some possible problem. So hopefully you watched the approach video here, because we're going to implement that recursive strategy and then memoize it. And so I'll start with a base case here. I know that if my amount is 0, then I can always generate 0, right? How can you generate 0? To generate an amount of 0, simply take no numbers of the array. It's sort of like the empty sum. So I would consider 0 possible as an amount, so I'm going to return true. That's going to be true regardless of whether or not what numbers are inside. That's actually a test case over here, right? If they give me an amount of 0 and even no numbers, it's still possible, right? Just add 0 numbers of the array together and you'll be good to go. So that's going to serve as a nice base case for me returning true. And let's go ahead and now iterate through possible numbers, right? So I'm going to iterate through all of the options I can take right now. So I'm I'm going to say for num in numbers. So this would just be iterating through this array. And what I want to do is take this first iteration of 5 and subtract it from this 8. That would give me 3. Then I could make a recursive call using that 3. So here's where I work in my recursion. I call the same function subpossible, give it my next amount, which I'm going to get by doing amount, the current one, right, and subtracting num from it. So again, what's happening here, let's say we're in this scenario where amount is 8 and my num is 5. I do 8 minus 5, so I'm passing 3 into this recursive call. Then I'm asking, is 3 possible using the numbers of the array? And so what we'll do here is also be sure to pass in the same numbers. I don't need to modify the numbers list because they tell me that I can reuse numbers as many times as I need. So that should be good to go. But now what I want to do is think about the return type of this function. Right? So here's where I do my recursive leap of faith. I'm going to assume my function's working. And if this call worked, then I would get back a Boolean, right? Telling me whether or not this quantity is possible, right? Can I make this quantity? And I'll check if that is true, if that quantity is possible, be explicit here, then what I should do is also return true. On the flip side, let's say that this call returned false. Well, then I just want to go to the next iteration of this for loop and check if the next number is a better choice. That means after our for loop, we do want to return false, right? That would mean that, all right, it's not possible to actually use any of these numbers in a way that would lead to my amounts being made, right, being summed up. So it's a very common programming pattern, right? Doing some recursion as well as some if statement inside in our loop. And what we want to do here is watch out for some errors, right? In some scenarios, maybe like this example over here, let's say that my current amount is 8, and I'm on the iteration of the for loop where my num is 12. And so if I do 8 minus 12, I'll get negative 4. And then from there, if I keep subtracting numbers of this array, I'll only get more and more negative numbers. And that can give me some infinite recursion. So what you could do is if you wanted to, you can check an if statement here and also check maybe around it or just use an and. You can always check if your number is less than or equal to your amount. That would be a fine way to implement it. What I'll choose to do here, and my favorite way to implement this pattern, is to actually add a base case. I'll just go ahead up here, check if my amount ever reaches something less than 0, then I can return false. Notice that this still catches this scenario because let's say I did pass negative 4 over here. Well then, in that call, I know it would automatically return false, and then I'll just skip over that number and go on to the next number. All right, I think we're ready to go ahead and test this one. Let's give it a shot together. So we'll give that a test run. And we expect this to at least time out because it is a brute force solution, right? So we pass a bunch of test cases, but toward the last few test cases, they give us some pretty large inputs. Right, so if I look at test 07, that's the first thing I time out on. So I'm not giving any incorrect answer, it just takes too long, right? Example 7 has me find a sum for 271, which isn't really a large number, but in the context of the runtime of our algorithm, it could be some large quantity. Right? Something we can recognize about this function right now is it's going to have an exponential runtime. If we say that a is the amount and n is the length of the numbers, I will have an n to the a runtime, which is exponential. And typically exponential functions are going to have a way too large growth. So to fix this, we'll use that memoization strategy, which is one way we can implement dynamic programming. And it'll be our go-to, I think, for much of this course. So what I can do here is maybe break out into a helper function, because I know I need to give a nice memo dictionary to this recursion, right? So maybe I'll rename this function, be careful with my refactor here, to underscore, some possible. Then in my main function, I could just redefine it, because they do want a function with this exact name so they can run the test cases. And the upshot of this is I can now return maybe just a call to that helper function, and I can give it some proper arguments, right? So some possible, pass along the amount in numbers, that's fine, and then give it an empty dictionary to be this memo. Nice. And now I actually want to use this memo. So some classic base cases. By now, this should be a familiar pattern, right? Being very inspired by patterns like fib. To me, it's a really core recursive pattern. What I want to do here is check if the amount is in the memo. Keys of my memo dictionary are going to be the amount. And how do I know to make it the amount and not the numbers? Well, amount is actually the thing that changes over time, right? I actually make amount smaller and smaller by subtracting from it. I can reuse numbers as much as possible so they don't change, right? So it's really the amount that drives the result of these recursive calls, right? So if the amount is in the memo as a key, then I want to return the stored values. So I'll return memo at amount. So this will get the corresponding value from that dictionary. And now what I want to be sure to do is pass this memo along to these recursive calls, because I want it to be shared by the entire recursion tree. And then I need to actually write some lines that store information in the memo. And what I always do is I look at my non-base case code. So I look at the recursive portion of my code. And whenever I had a return statement, I'm going to actually store that value into the memo first before returning. So that would look like this. I look at this first return. And right before I return, take that value and put it as the value inside of the memo. So I'll say memo at amount. An important thing to do here, I always, if I do this recursively, want to store the key as the plain argument. So I'm not going to do something like this. This is not what you should do. Because with memoization, what you're saying is, as the values of my memo, I want to store the results for this recursive call. And this recursive call is about amount. Right? If you wrote it about amount minus num, then technically you're expressing it about your child recursive call. So you want to do it just like this. So just take your plain argument, add that in. Then I'll do something very similar for this return false. That'll be a nice recipe you can always use. So I'm storing information in this memo in case someone needs it later on. In other words, if someone encounters this same amount, well, then I have this information. They don't need to recalculate it fully. Just look at this memo, because if it's a dictionary, it's a constant time insertion, but also a constant time lookup over here. So let's see this run now. Awesome, and there's a perfect solution for this sum possible problem. At this point, we brought our runtime down from an exponential down to a linear, so I would be looking at an a times n runtime. Space complexity here is also going to be a linear in the amount. And that's because if you think about it, I store a different keys within my dictionary over time, and even in terms of the recursive call stack used, I know in the worst case, the height or the maximal stack depth of that recursion is going to be a, right? Imagine the worst case, I kept doing -1 as my numbers, in which case the height of the tree would be exactly a. All right, programmers, I really want you to practice this pattern because we're going to do a lot of similar dynamic programming problems coming right up. So this is a really, really core pattern. It's okay if it's a little confusing right now. You will learn to master it through some repetition. Do try to notice how it's similar to our previous fib and trib problems though, right? I'll see you in the next one.
Hey programmers, I wanted to take a quick break from dynamic programming to tell you about my complete data structures and algorithms course at structy.net. The DP material you've been working through thus far is actually taken straight from my course at structy.net. Dynamic programming is one of the later topics, but in my full course, I'll teach you everything you need to know to pass your full interviews. This includes topics like sliding window, binary trees, graphs, and much more. The best part is, I'll be there to explain each problem using the same clear animations and code walkthroughs that you're used to. That's structy.net. I'll leave a link in the video description if you're interested. And now, back to our course on dynamic programming.
Hey programmers, Alvin here. Right now, let's go over the approach for this min change problem. So in this problem, what we want to do is take in two things as input. We're going to be given a target amount as well as an array containing some coin values. And what we want to do is return the minimum number of coins required to create the amount. So for example, since my target amount is 5, one way I can give back 5 cents would be to do 1 plus 1 plus 1 plus 1, or I can do 1 plus 2 plus 2, or I could even do 1 plus 1 plus 3, and also 2 plus 3. In this problem, what we want to do is choose the way that requires the least number of coins. So that would be the 2 plus 3. That would use only 2 total coins. And my function should just return that number of coins, which would be 2 as my final answer. All right, so let's start attacking this one by visualizing it. Let's sketch out what we would do for an amount of 4. That way we can actually finish it, because we're going to see that as we moderately increase the amount, the size of our problem actually grows pretty large. And so if you're doing all of these problems in order, and I always recommend that you do, you should recognize this one as a dynamic programming problem. So what I'm going to try to do is shrink my problem size, then also notice any overlapping subproblems in the long run. And so I'm going to sketch things out as a tree. What I'll do in the nodes of my tree is write down my current amount that I need to generate. And I can break my current amount down into smaller subamounts. So let's say I start with 4 at my root. To generate an amount of 4, what I could do is use a 1 cent coin. And if I did that, my remaining quantity would be 3 as my amount. I could have also taken a 2, in which case I need to generate 2, or I could have taken a 3 cent coin, in which case my remaining amount would have been 1. So let's continue this pattern. Let's say I was at this 3 node. This node would have 3 more children, just branching for 1 cent, 2 cent, and 3 cent respectively. If I take a look at this 2 node over here, I can't actually use every option here. I should only branch twice. Because if I took the 3-cent coin, that would give me a remaining amount of -1, which I should probably avoid. Similarly, for this node of 1, I can only branch using the 1-cent coin. So let's say we continue this pattern for the entire tree, you would end up with this structure. And what we see visually is the decision tree that represents every choice of coin we can make until we hit 0. And so this is a tree structure that we've seen a few times in the course. What I'm going to argue is within the visual of this tree, you should actually be able to recognize what the answer is for this amount of 4. So take a moment, see if you can recognize any properties within this tree. Where can I find the answer to this problem? What we should do is interpret each path of this tree. So let's say I looked at this path. That would represent the sum of 1 plus 2 plus 1. In other words, I took a 1-cent coin and a 2-cent coin and then another 1-cent coin. And what I can say is that would represent the answer of 3, like a possible answer of 3, because I used 3 coins to generate my target amount of 4. That's only one possibility. We know in this problem we really want the minimal number of coins used. So that should translate into one of these shortest paths like this one. This would represent my sum of 3 plus 1, and that would have a length of 2. You can probably notice that there are a few other paths with a length of 2, but that's okay. We just want to return the smallest length possible, which would be 2. And so what we're really recognizing here is the minimum number of coins required to generate our amount would really be the shortest path from the root to any leaf within this tree, assuming a leaf terminates at a 0. So how can I do this more programmatically? Maybe we'll sketch this out as some recursion tree, right? So what I'll do is think of a return value for all of these 0 nodes. What we can say is our base case, if our amount is 0, then I should return 0. And so 0 is a great choice because it's a small number and I can't break it down any further. And I should also return 0 for that instance because the minimum number of coins required to make 0 cents would be to use 0 coins, right? Just use no coins. So above all of these base case nodes, I'm going to jot down my result of 0. And what I can do is start to evaluate these as return values. So let's say I was at this node of 1 over here. What I'll do is just receive 0 from my child call. What I should also do is add 1 to it. If I add 1, that would actually count the edge between myself and my child node. Because remember, when it comes to counting the number of coins, we're really counting the number of edges in a path through this visual tree. So let's say I was at this 2 node now. I was ready to evaluate it. What I do is receive both of these values of 1 and 0 for my children. And because I want the shortest path, or the minimum number of coins, my node needs to choose the smaller between the two. So I do 1 versus 0. I pick the smaller one of 0. But then what I need to do is actually increment that by 1 to count the edge between us. And what that would represent, this 1 designates the shortest way I can make 2 cents, which would represent this path highlighted in pink. Let's continue this pattern. So let's say I was at this 1 node, the 0 would just bubble up, then I add 1 to it because there's no decision to make. But now I can be at this 3 node. This 3 node is going to receive 3 options. It's going to choose the smallest among them, so just 0, but then it needs to add 1 to it. And at this point, I should be able to check for correctness. I have a green number of 1 above my 3 node, which means the minimum number of coins I need to make 3 cents would be just using 1 coin, which makes perfect logical sense because I have a 3 available in my coins array, so I could just take a single 3-cent coin. Let's continue this pattern elsewhere in the tree. At the root node of 4 in this tree, it's going to receive a bunch of 1s. Technically, it would choose the smallest among them, which would be a tie, given 1. And what I should do is always increment it by 1 to count the edge between myself and the children nodes. And this 2 represents the fact that I have a few different paths that could only take 2 coins, or 2 edges. It could represent this path, or even this path. So as we evaluated this tree, something really important we did was whenever we received multiple values from our children, so when we received multiple sub-solutions, what I do is choose the smallest among them, right? I know I need some min value logic present in this implementation because I want to choose the minimum number of coins possible. So I'll just keep that in mind when we implement the code. When we talk about the complexity of this, we've seen the structure before. Right now, we're going to describe the brute force complexity. If we say that C is the length of the coins array and A is the target amount, then the time complexity is going to be exponential, right? We know that the branching factor of this tree is going to be based on the number of coins, so C, right? Branching factor refers to, given a node, at most, how many times will it yield children? And I know my branching factor here is 3, and in the worst case, I have 3 branches coming out of a single node. My exponent here is going to be a, because that would be the height of the tree. We'll say that the space complexity is going to be O of a due to the call stack, because if you look at the height of this tree, it would be in the worst case a. We say the worst case would be the scenario where I keep taking a bunch of 1-cent coins, giving me the deepest recursion possible. So if you start at the root node here and you just keep going left, you're going to see a sequence like 4, 3, 2, 1, 0, and that definitely is a linear pattern in A. So overall, we're looking at exponential runtime and a linear space complexity for this solution. The time complexity definitely needs some work though, right? We want to bring it down from an exponential. So like we usually do, we just want to memoize this one. We'll try to notice any duplicate subproblems. So looking at this tree, there are some duplicate subtrees I can notice. I can see these subtrees rooted in 2. So instead of recalculating that subsolution, I can save it and just reuse it. So I can trim out that piece of the tree. And I also have other subtrees rooted in 1. And I can also ignore those, right? The way I'll implement this is by using some constant time data structure like a hash map. I can store sub-results as I compute them in that hash map and then reuse them later on. If that high-level strategy seems confusing, don't worry, you'll want to wait until the walkthrough video where I actually show you the details on how to implement this in some code. So let's do a reanalysis of this. Now we're going to analyze this dynamic programming solution that uses memoization. The time complexity is just going to be a times c, so it's no longer exponential. It's really a sort of multilinear, right? Just multiplying my 2 terms together. We know the time complexity is going to be based on the number of recursive calls we make, and in this visual diagram, every node represents a recursive call. We still have a tree of height a, so that's where the a comes from. And what we're saying is, across every level of this tree, we have at most c nodes. So I think of a as the height and c as the width, and that would give me a times c nodes overall. And it's actually pretty easy to spot in this particular example. In the worst case scenario, at a particular level, we have only 3 nodes at most. That's because our coin array only has 3 options inside of it. The space complexity for a solution is just going to be O of a due to the call stack, and we'd be storing at most a different keys inside of our memo hash map. All right, I think I'm ready to code this one up. You'll want to join me in the walkthrough video now. Hey programmers, Alvin here. Right now let's go over the Python solution for this min change problem. So do make sure you watch the approach video first, and we'll solve this recursively, of course. And so I'll begin with my base case here. And so very similar to our last problem, if our amount hits 0, then I know that I actually could create that amount. And the trick here is to return 0. And why is that logical? What we're saying is, if you ask me the minimum number of coins required to make 0 cents, I would just tell you 0, right? Just use no coins. And so that'll be my base case. And for now, let me set up my recursion. So I know that I have a base case about a trivially small amount. In general, amount's going to come in as a large number. And that means I need to decrement the amount over time. So just some subtraction. And I'm going to subtract a choice of coin from that amount. So I'm going to iterate through every coin I can use. I'll say for coin in coins. So for every coin, what I want to do is make a recursive call, right? Min change over here. And to get my next amount, I'd take my current amount and subtract that coin. And this feels good because I am approaching 0 now, right? If I keep subtracting some numbers, I will get closer and closer to 0. I can pass along the same coins list because I don't need to remove anything from coins because I can reuse them as much as I want. And at this point, I think about the return type of this function, right? I do my recursive leap of faith, right? What type do I get back from this? This function should give me a number representing the minimum number of coins used to make this remaining quantity, right? So for this number of coins used, if I add 1 to it, then that would represent how many coins I need to generate my amount. Right? And at this point, I have this possibility. This would be one way. I'll call it my num coins. But I know through some other iterations of this for loop, I would have other possibilities. And they could all give me a different number of coins used to generate their amounts. What I'll want to do is actually take the minimum among them. So I just need some min value logic here. What I could say is create some min variable, I'll say min coins. And I have to think about a clever default value. Because I want minimization logic, I think a good default would be positive infinity. To represent that programmatically in Python, you can use float, and then you pass in the string inf, represents positive infinity. If you wanted negative infinity, you can do this, right? And so I'm going to default min coins to infinity. That way, when I encounter some valid number of coins, I can immediately replace it just using some classic min value logic. So I can just say, all right, if the number of coins that I just attempted, if that is smaller than min coins, Well, then I have a new min coins now, right? So I could do min coins equals num coins. Classic min value logic. Then after my for loop, I should be able to just return the minimum number of coins. So that should give us the shape of a brute force algorithm. Tricky thing with this algorithm is usually trying to understand why we do 1 plus here, right? I'm adding a 1 to count this coin that I've just chosen, right? And so that feels pretty good. Let's go ahead and test this. We'll have to correct some edge cases, but it's worth trying. So here I'm getting an error, maximum recursion depth exceeded in comparison. So I'm getting infinite recursion. That's going to happen because I'm not blocking any negative quantities for amount. So imagine I had this scenario. If I had my amount as 8 and my current coin that I was iterating through was 12, if I do 8 minus 12, that would give me a next quantity of negative 4. And then from there, on the next iteration, or the next call, I would just subtract something else from that. So it's going to get more and more negative, and it's never going to get stopped by this base case. So the way I usually capture this scenario is with a base case up top. I can check if the amount ever goes negative. So if the amount is less than 0, then what I want to do is basically say that, all right, something went wrong, so return something invalid. So what I would do here is return float infinity. And why is that a good choice, right? So let's say that I was on that iteration, like I said, where amount is 8 and my coin is going to be 12. So that means I make this call and I pass along a negative 4 like this. I know that this call is going to be caught by this base case, so it's going to come back as infinity. When I do 1 plus infinity, that's still infinity, and I know that that would not be less than whatever I have currently stored in min coins. So I basically ignore it, which feels good. So we'll bring it back to the original code. And I think we're ready to give it another test run here. Added a little base case. And it looks like we're passing some of them, but we are going to time out, right? And this is kind of what we expect because this is a brute force algorithm. Like you guessed, this is going to be so far an exponential runtime. So you know the trick by now. Let's go ahead and memoize this. So what I'll do is split this into a helper function. So this will be my helper because it does the recursion. And for the main function, that'll be my original min change, plain old. And what I'll do is call this function and pass along exactly what I need. So the amount, the coins, and now my memo object. I'm going to use a dictionary, right? I should actually just pass it in line here. Then I can take it as an argument on line 4. And now I write my classic memoization logic. And this is a formula you're going to see me write many times, and you've seen me write a few times before. I always write the brute force, because afterwards, making sure the brute force is correct is just a matter of testing the code if you have the opportunity. Then I just change a few lines using a memo to make it faster. But I think implementing the brute force is always a natural step along the way to memoizing a more efficient solution, right? So I never skip the brute force. And so at this point, what I'll do is I'm going to check as a base case. If I've seen this amount before, then I should return the value stored in the memo dictionary, right? Here, I'm going to just use the amount as the key of my memo dictionary because coins doesn't change. So it doesn't really dictate too much about the answer of this recursive call. The amount does, though. I know the amount changes over time. And now I think about where I need to pass the memo. So pass it in this recursive call. That way it's shared among the entire recursion tree. And where I store my subresult into the memo should be exactly where I return. So I'm going to save stuff into the memo on this return line. So I don't need to do it inside of the for loop. Something I always feel strongly about when you're memoizing something, just locate your return lines and memoize that expression. That's a surefire way to memoize this. So I'm going to say memo of the amount, being sure to use my original amount, right? Don't use amount minus coin as your key. In other words, this is wrong. So just use amount, then assign what you just returned. And be sure to still complete the return. That way you can still get the value up here when you need it. Remember, this is recursive, meaning this function refers to itself. So that feels pretty good. We have a little bit of memoization logic now. Let's test it. Should be one more edge case we need to work on. And yeah, it looks like test 0.5. They expect -1, but we gave back INF. It looks like we gave back infinity, so we should probably think about something happening here. If I think about test 0.5, that's actually a scenario where it's not possible to generate this amount. right? And in the problem, they say if it's not possible, you should return -1. In the case of our code, just using our plain old recursion, because we're using infinity here, float infinity, that infinity is actually going to come back into our main function whenever something is not possible to be generated. And so what I'll do is maybe just catch it over here. So I'll say, all right, this is the answer I get. And if the answer is infinity, so I can check float infinity, then return -1 is really what they want to represent it, right? Otherwise, I'll just return the plain answer. And that should be good to go. So let's give that a test run again. Awesome, and there's a solution for this min change problem. At this point, our algorithm does have a multilinear runtime, right? It's going to be A times C. Hey programmers, Alvin here. Right now, let's go over the approach for this count paths problem. So in this problem, we're going to be given a grid. What we want to do is travel from the top left corner down to the bottom right corner. And here we want to return the number of ways that's possible to traverse through this grid. And the caveat is we can only move to the right or downward. That means we can't go up and we can't go to the left. And so for this particular grid, let's talk about the different ways we can travel through it. One way would be to go right, right, down. Another way would be to go right, down, right. And finally, the last way would be to go down, right, right. And since there are 3 possible ways to travel through this grid, we should just return the number of 3. So this should be a counting problem for us. However, this problem is a little more nuanced. They say that some positions are going to be occupied by walls and we can't travel through them. So if I had a wall like this in the top right corner, then one way to travel through the grid would be right, down, right, and the only other way would be down, right, right. So let's trace through the strategy for this one by looking at a larger example. If I was given this 3x3 grid, I'll also put a wall in the top right corner. Let's start by labeling the indices for our rows and columns. We know that we start in the top left corner, so that would mean row 0, column 0. And what I want to start to do is try to give myself a way where I can denote every option I have, right? How can I mark the decisions I can make by traveling through this grid? So I'm going to visualize this one as a tree. So if I start at position 0, 0, I can make that the root of my tree. If I'm at this position, I'll think about my options that I have. I can either move downward. If I move downward, that would increase my row by 1, but keep my column the same, giving me 1, 0. Or if I went to the right, I keep my row the same at 0, and I increase my column by 1. And that would be the only 2 options I have from this root position. And I can just apply this logic recursively. So let's say I was situated at the 0, 1 node right now. So I'm over here. I know that my options are more limited now. I can't move to the right because I have a wall in my way. So I'm going to need to make sure I code that one up. And I can only move downward here. And that would mean increasing my row by 1 and keeping the column the same. And so let's carry over this pattern to draw out the rest of this tree. We know that given a node, at most it's going to have 2 children, representing my downward or rightward movement, and that would mean either incrementing the row by exactly 1 or incrementing the column by 1. However, we should not do that move if we go out of bounds or run into a wall. So the full tree would look something like this. What's great about this tree is if I start at the root and travel to a leaf node, that would represent one of the paths I can take through my grid. In other words, if I look at this path in my grid, I can represent that using this path in my tree, which is a really nice way to interpret this problem. And so let's start to realize how we can encode the base case in this problem. What you should be realizing is we're visualizing this as a tree, which usually gives us a nice way to implement this as recursion, right? So if I look at all the leaf nodes here, I always terminate at 2, 2, because that would represent the bottom right corner of my grid, which is the goal. And so if I'm at the bottom right position of 2, 2, what should I do here? Well, I have to think about the return value for my function here, right? They say they want a count. And so what I should do is treat this 2, 2 position as if it's its own input. So if someone asks me in how many ways can you get from the bottom right position to the bottom right position, the answer would be 1, right? There's only one way to do that, and that would be to just stay there, right? Because you're already at your goal point. And so I'm going to make all of these leaf nodes or all these base cases return 1. And having these calls return 1 seems useful because I know I need to tally up a count in this problem. So how would we start reconstructing our larger solutions here? Well, I would just really bubble up these ones, right? So let's slow down at this 1, 1 node over here. We know that this node has a little more work to do because it's going to receive 2 values. And so what I should do is bubble up both of these values, right? And then this node should just add them together. So 1 plus 1 gives me 2. And so what are we saying here? If I pause, I should have some logical information in this subtree. What it should be saying is that there are two ways to get from the position 1, 1 to the bottom right corner. I have this path, or I have this path. There are two different ways to get from 1, 1 down to your bottom right corner. So I'll just carry over this pattern, keep reconstructing all of my solutions. And as we get toward the top of our tree, we are going to get the final count of all of the ways to travel from the top left to the bottom right, giving us our final answer of 5. What's great about visualizing this one as a tree is it really describes the decisions we can make as we travel through the grid, right? We know that this gives us a binary tree because for the most part, when we're on the inside of the grid, we only have two options, right? You can either move downward or to the right. And that'll help us decide the complexity of this brute force algorithm. So if we implement this algorithm as it is, just with some baseline recursion, we say that R is the number of rows and C is the number of columns. This will give us an exponential runtime, meaning there are an exponential number of nodes in this tree. Really, it's 2 to the R plus C power. So the base of 2 comes from the fact that this is a binary tree, and in the context of our problem, that means I can only move downward or to the right, so you only have two options. And I'm saying that the height of this tree is R plus C, right? Because you know you want to start in the top left corner, 0, 0, and travel to the bottom right corner, what you have to do is actually traverse a path that is exactly R plus C moves along, right? Because you need to move through all of your rows and all of your columns. For the same reason, I can say that the space complexity is going to be R plus C just due to the stack depth, right? Stack depth is equal to the height of this tree, which we just said is roughly R plus C. And so overall, we shouldn't be too satisfied with the time complexity of this one, right? Typically, something exponential would be too slow for our liking. And so what we should do is recognize that we actually have this visualized as a nice dynamic programming problem. What you should do is take a moment, look at our visual tree, and notice if you can spot any duplicate subproblems, right? Are there any overlapping subproblems here that I can memoize? So we actually have a duplicate subtree over here rooted in 1, 1. What I could do is just save the first time I calculate it. That way I don't have to fully recurse down my tree the second time around, effectively memoizing my duplicate function calls, which in the context of my tree visual just means that I prune out some branches. There are some other subtrees here. I can look at this 2, 1 subtree. I can also memoize that away. And we know as we grow the problem size, in other words, if someone gave me a larger and larger grid, I would have more and more overlapping subproblems, so I'd benefit more and more from memoization. Like usual for us, the way we'll implement this is by using some hash map data structure. I'll save that detail for the code walkthrough though. So what do we know about the new and improved complexity of this one, right? We're going to implement our dynamic programming using our classic memoization strategy. So like usual, R is the number of rows and C is the number of columns. Now it would be the case that our time complexity is R times C, right? It's still the case that our time complexity is driven by the number of recursive calls we make. And now we would be making roughly R times C different recursive calls, right? And how do I know that? Well, in the context of what I'm going to memoize into my hash map, I'm going to put positions, right? Notice that each node in this visual is a position of row and column. And I know that there are exactly R times C different rows and columns. So once I store a row and column into my memo, I would never have to fully recompute it, which gives me my time complexity of R times C. Likewise, now is the case that my space complexity is R times C, taken mostly from the size of that memo, right? Every position is going to be a key, and so I have R times C different keys in my memo object. All right, programmers, I'm sure you're itching to see how we actually implement this one in some code. So right now you'll want to join me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now let's go over the Python solution for this count paths problem. So like we said in the approach video, we're going to solve this one as a dynamic programming problem. We're going to do this recursively, that way we can memoize it in the long run. We'll start with a brute force solution. What I want to do is set up some infrastructure so I can begin in the top left corner of this grid. So what I'll do is maybe I'll take in some optional arguments here, maybe some row and column. I think I'll actually split this up into maybe a main function and a helper function that is recursive. So I changed my mind here. Let's make the helper function, and I'll name it underscore count paths. And this helper function is going to do the recursion, so it is going to take in a row and column, which means when I actually invoke that helper function, I'm going to give it the grid as well as my starting position, which would be the top left corner, 0, 0. And whatever answer this gives me back, I'm just going to return that as my final answer. So now I want to do all of my work inside of this little helper function. Let's start by laying down our base case, and we need a few different ones. What I'll do is start by handling the scenario if I step out of bounds, right? So in this problem, we can only move to the right and downward, meaning we can't go up and we can't go to the left. So when I check for inbounds, I only need to make sure that I don't fall off the right edge and I don't fall off the bottom edge. So for me, that's pretty straightforward. I can check, all right, if my row, if it's equal to the length of the grid, if this condition is true, that means that I'm out of bounds on a row, right? Because I know that the final valid row would be at index length minus 1. So that's if my row's out of bounds, or if my column is out of bounds. I do want to access the inner number of columns here. All right, so if my row is out of bounds or my column is out of bounds, then what I should do is return a value. And what I want to do here is overall get some counting logic. So I think I'll return 0 here because I don't want to count any paths that lead out of bounds, of course. So I'm going to return 0 here. Then from there, I need another base case to actually check if I hit my target, right? My goal is the bottom right corner, so I'm going to check, all right, if my row is the last row, so equals length of grid minus 1. So this would refer to the very last row, and I'm in the last column. And so if I'm in the bottom right corner, then what I want to do is count this as 1, right? And recursively, if I think about this, what this question is trying to ask is, all right, if I'm already in the bottom right corner, in how many ways can I get to the bottom right corner? Well, there's just one way, right? Your base cases should also be correct in themselves if you treat them as if they're their own input, right? So there's only one way to get from the bottom right corner to the bottom right corner, and that is to do nothing. And now what I want to do is progress my position toward that bottom right corner. So if I was moving down, I'll do count paths of grid of row plus 1, keep the column the same. If I was moving to the right, I would add 1 to the column, keep the row the same. Nice. So these two calls will make progress toward hitting my base case. And what I want to do is think about what these function calls return, right? So because I'm solving this recursively, I'm going to assume my function works. This should give me the number of paths to get to the target by going downward. And this will give me the number of paths to get to the target if I move to the right. So I'll call this my maybe down count. And I'll also save my right count. And I want the total number of ways, so I would just add them together. So I'm just going to return my down count plus the right count. If I count the number of ways moving downward from here and the number of ways moving rightward from here, that'll give me the total number of ways either moving downward or to the right. So this looks like some good counting logic. I think we might be ready to test this code as it is. So I'll give myself some room over here. What we're looking for right now is to at least pass the first few test cases. So we'll give this a shot. So it looks like we're passing 0, 0, but we're not passing 0, 1. If you look at example 0, 1, it's an example where they actually place a wall on the grid, and we didn't actually take that into account yet. And so I'm going to add a base case to handle this scenario, right? What if I hit a wall? And I can really treat that as part of this condition here. So here I'm going to return 0, basically representing an invalid path if I'm out of bounds, or maybe I'm in bounds, but my position is an X, right? Because X's represent walls. So if my grid at row column, if that is an X, then I'll also return 0, basically avoiding the count for those paths. So let's try that again. Again, we're passing a few more examples, and we are going to time out for this one. Like we expect, as it stands right now, like we said in the approach video, this is going to be an exponential solution, right? Because what's going to happen is I'm going to basically have some duplicate traversals to some positions of row and column. And what I should do is save that sub-solution for later on. So we'll work in our memoization here. What I'll do is start by passing in an empty dictionary as my memo, in which case I can receive it over here. Cool. Key thing about this problem is, and in general for memoization, once I have the brute force recursion, I want to make the keys of my memo the arguments to my function that actually change, right? So the grid itself does not change through this recursion, right? I always pass along the same grid. Arguments that do change are row and column. And I need to use both the row and column as like a combination as a key in my memo. And so what I'll do is I can just use a tuple here, just a pair of the row and column. I'll call that my position, and that's going to be the key into my memo. So I'm going to check at the top. All right, if I've seen this position before, so if the position is in the memo, then return the stored value of it. Classic memoization. And then I just jump right to my function calls over here that are recursive, and I share the memo for all of those calls. And where do I add information into my memo? That should just be a matter of changing my return line here. So I know that this was my old return value. I'm going to take that value and store it in the memo using this key, using this position, then I still want to complete the return. So just return this as well. Do bear in mind that we're storing both the row and the column as a pair as the keys of our memo. That's really important here. So that means if we looked at like the entries in our memo, every position that corresponds with some subresult would tell me, the number of ways I can start at that position and then go to the bottom right corner. So let's try that now. Awesome, and there's a solution for this count paths problem. Now it is the case that we brought down our complexity down to something that's linear, which is a really fast solution. All right, programmers, so hopefully you're starting to notice how we can use dynamic programming and memoization to solve some really diverse problems, right? Previously, we've solved some problems like coin change, but now we're dealing with pretty different structures like traveling through a grid. But if I can tackle a problem using some brute force recursion and I can notice any overlapping subproblems, then I'll always choose to memoize it in this way. All right, programmers, be sure to practice this one before moving on to the next problem because we're going to increase the difficulty. I'll see you there. Hey programmers, Alvin here. Right now let's go over the approach for this max path sum problem. So in this problem, we're going to be given a grid and we start in the top left corner and we want to make our way to the bottom right corner. This grid's going to be populated with some numbers though. What we want to do here is return the path containing the maximal path sum. In other words, there are a few ways we can travel through this grid. One way would be to use this path, in which case your sum would be 14. Another way would be to use this path, in which case your sum would be 12. And finally, you can use this path, in which case your sum would be 18. And between these three options, I should choose the 18, right? And so that would be the max path sum for this grid. So let's cut to the chase and describe the strategy for this one. And we'll step through exactly this example. So we'll label the row and columns. And we also know that we start, of course, in the top left corner. This is really just a spin-off of our last problem. So hopefully you visualize this one as a tree, right? A binary tree, because we only have two options at any point in time, right? You can either move downward or to the right. And sometimes in just one of those directions, depending on whether or not you're at the border of our grid, right? So we'll start at 0, 0. From this position, I have two options. If I went downward, I would increase my row by 1. Notice that each pair within a node here is a row and column. Or I could have moved to the right, in which case I would be at 0, 1. Now to represent my two moves. Let's say I was situated at this 1, 0 node. Here I only have one move possible to make. I must move to 1, 1, right? That represents a move to the right. If you look at my row and column indices, that's because I can't go downward anymore because I'm already in the last row. If I take a look at this position over here, I do have two options, right? I can go downward or to the right, giving me 1, 1 and 0, 2 respectively. And we can build out the full tree from this point. We know that we must terminate at position 1, 2 because that would be the bottom right corner. So I know that that is our ending point, right? So that's going to be my base case. I know in this problem I want to choose the maximal path sum, so I want a max sum, but how can I start accumulating a sum in the first place? And so what you have to do is ask yourself, if I'm already at the end position, what is its max path sum to the end position? And that would just be the value of 2, right? That's exactly the number in that ending position. So for my base cases, I'm just going to return whatever number is in that final position. Then from here, I know that these values are going to return. So let's say we were situated at this 1, 1 node. It's going to receive a value from its child call because we know we're visualizing this in a recursive way. And what I should do here is note what position I'm at. So 1, 1 would be this position containing a 6. I want to accumulate a sum here, so I should do 2 plus 6, giving me 8. So this node's going to return 8 to its parent. So this 8's going to bubble up a little bit more. And if I think about this 1, 0 node, that represents my current value of 5 over in yellow. And I would do my 8 plus 5, giving me 13. So that would be a partial path so far. So we'll continue this process on our right-hand side. We know that these would just bubble up, and we would add the respective values at those positions. Things get more interesting when we're at this 0, 1 node though. So for this node, it's going to receive both 8 and 14, right? It's just going to return back up like we always do. And I have to make a decision here. Since I want the max path sum, this node should choose the larger of those two values. So 14 is bigger than 8, so I prefer the 14 here. But I should also still add the value stored at my current position. So if I look at position 0, 1 within my grid, that would be this value of 3. So I add 3 to the 14, giving me 17. And finally, this takes place again at the root. So if I'm at 0, 0, I'm going to receive the 13 and the 17 for my children. I choose the bigger value of 17, and then I add my position itself, which has a value of 1 inside. And that gives me a final answer of 18. So the way we reconstructed our sub-solutions into higher level solutions was to choose the larger of our two children and then add ourselves to it. That way I get some max value logic while also summing our path. We talk about the brute force complexity of this algorithm. We say that R is the number of rows and C is the number of columns, then our time complexity is going to be exponential, just like we saw in the last problem. The base of 2 comes from the fact that given any position, we have two options, right? We can either go down or to the right. And I make R plus C the exponent because that would be the height of this tree, right? That would be the length of any particular path. I know any path that travels from the top left to the bottom right must cover all of the rows, R, and all of the columns, C. And so the entire path length would be R plus C. In a similar way, I'll say the space complexity is R plus C due to the stack space required by this recursion, right? If the height of this tree is R plus C, that means the stack space used by my recursion is also going to be R plus C. But a keen observer would note that I can do better because this is a dynamic programming problem. So what I'll do is take a moment, look at this tree, see if you can find any overlapping subproblems. And although this example was small, I can already see some overlap. If I look at this node rooted in 1, 1, I see it here, and I also see it here. And we know the punchline is I should only have to calculate these nodes exactly once. So I should be able to trim out a little bit of the tree by using some memoization. And as we actually increase the size of our input, as I get a larger and larger grid, I would have more and more overlap that I'm able to kind of forego using some memoization. Like usual, we're going to implement this using a hash map, but I'll save those finer implementation details in the walkthrough video. If we implement memoization properly for this one, we're going to bring our complexity down to linear, right? So we're going to have a time complexity of R times C. And that's because there are R times C different nodes to actually cover now. Right? I know I'm going to put the positions as the keys of my memo, and there are R times C unique positions. In a similar way, it's now the case that my space complexity is taken over by the size of my memo, which is also R times C because of the number of keys, right? I have R times C keys because I have R times C positions. All right, I think I'm ready to code this one up. You'll want to join me in the walkthrough videos now. Hey programmers, Alvin here. Right now, let's go over the Python solution for this max path sum problem. So like we said in the approach video, we're going to solve this one as a dynamic programming problem, which means we'll start with some brute force recursion, and then we can memoize it in the long run. So what I'll do here is start by assuming I have a helper function. I'll call it max or underscore max path sum. That way I can feed it some additional arguments because I need to know my current position. And at the start, I begin at position 0, 0, right? Row 0, column 0. So now I'll write that helper function that actually performs the meat of the work here. So I'll start with my base case. I do want to check if I'm in bounds. And so what I'll do is check, all right, if my row is equal to the length of the grid, then that means I'm out of bounds along the row. So I made it just past the bottom edge. Or I can check my column if that's equal to the length of the inner grid. And that would tell me if I'm just past the right border. So if I'm out of bounds in either my row or my column, then you should return some like invalid value. Because I want to find the maximum path sum over time, a good value to return here for something like invalid would be to return negative infinity. So for me in Python, that'll be float. I pass negative INF like this. I know because I'm going to do some max value logic over time, whenever I have to choose among like a negative infinity, I'm never going to choose that negative infinity because it's an arbitrarily small quantity. Nice. Now I need my like affirmative base case. I know my goal is to get to the bottom right corner, so I can check if my row is the last row. So I can almost just steal this condition. So to be in the last row, you should be at length of grid -1. And to be in the last column, you should be at length of grid 0 -1 as well. So this will check if I'm in the bottom right corner. Notice how I changed it to an and, right? So I must be in exactly the bottom right corner. If that's the case, I want to return that path sum. So what's the max path sum to get from the bottom right corner to the bottom right corner? Well, that would just mean you look at the value in that bottom right corner, right? If someone asks me how can I get from this position to the bottom right corner, since you're already there, the answer is just 1, right? That would be the max path sum. So what I'll do in this scenario is just return whatever I've stored at my current position. Nice. Now that I have my base cases, we need to work in that recursion, so call the same function again. And so in this problem, I can move downward, that would mean row +1, or I can move to the right, that would mean column +1. And I should always do my recursive leap of faith, right? So I'm going to assume these functions work, right? Although it's recursive. So this call will give me back the maximal path sum by traveling through my down neighbor. So I'll call it my down. And then this will give me my max path sum by traveling through my right neighbor. So I'll call that right. What I want to do is choose the bigger between them. So if I did max and I pass along down and right, that would choose the sum that is larger. And whatever sum that is larger, I want to add myself to it. Myself is row column, so I'll get my element, just like this, just index into the grid, and add it to the max between your down and right. And this logic does feel very reminiscent of what we stepped through in our visual tree in the approach video, right? I have two calls, right? That gives me like the binary tree nature of this problem. And then I choose the larger between them. And then I just add myself, and that would give me my final result. So this code is looking pretty good. Let's go ahead and give it a test run. This would be our brute force. So we should get some slow results for the latter test cases. Right now, this would be in the realm of an exponential. Yeah, it looks like we're timing out. It's like we always say, if you want to make this faster, then consider memoizing it, right? Because we know that there are some overlapping subproblems here as per our approach video. So for me, at this point, it's a very canned formula. This is why I always like to solve my dynamic programming problems using this like memoization strategy, because I can easily, most of the time, write a brute force recursion. And then after I understand that I have a correct solution and it's just slow, I should just be able to add a few lines to memoize it and make it faster. So it's always a little recipe for me. So I'm going to work in my memo dictionary, pass it in over here, and I can take it as an arg over here. And I want the keys of this memo to be positions, right? I think of the arguments that change here. The grid does not change over time through my recursion, but my row and column do. So my row and column need to become the keys of my memo. So I'll create a position, which would be just a tuple combination of that row and column. Now I can check, all right, if the position I've seen before, so if it's in the memo, then I would have stored a value inside to represent its result. Just return that stored value. Now I need to be sure that I pass that memo along all my recursion, so it's shared. And then wherever I did my return, I take that returned value, put it in the memo first, and then still complete the return. So I'm just going to go right to this return line, right? Only the recursive one. And I store that value as the memo at position, just using the same key, right? And then I just want to complete the return. So I can just return this, right? It's important that you still return that result because you're going to assume that it's returned recursively over here. Remember that this function is recursive, so it needs to refer to itself, right? So that's looking pretty good. Let's give it a shot now. And by doing our very classic memoization strategy, here we have a nice linear solution for max path sum. Hey programmers, Alvin here. Right now let's go over the approach for the summing squares problem. So the first thing we'll want to do is review what a perfect square is. You can create a perfect square by just taking some positive number and multiplying it by itself. In other words, I can do 1 times 1 to give me 1, 2 times 2 to give me 4, 3 by 3 to give me 9, and 4 by 4 to give me 16, and so on. So in this problem, we're going to take in a number as input, and we want to do is figure out the minimum perfect squares that sum up to our target number. So for this input of 12, the least number of perfect squares I can use would be doing 4 plus 4 plus 4. Notice that this is a valid perfect square sum because 4 is of course a perfect square. Another way that uses perfect squares to add up to 12 would be 9 plus 1 plus 1 plus 1. However, that would be a longer way. Right? I want to use the minimum number of perfect squares, and so here I should return the answer of 3. And the reason behind it is because I do 4 plus 4 plus 4, which is 3 perfect squares. All right, so how can we break down this problem? Let's step through the example as if our input was 10. I'm going to start at 10 at my root, and what I know I have to do is get this number to be smaller and smaller, because decreasing the size of our input would mean an easier and easier problem to solve. So what I have to do is subtract different perfect squares from this 10. So what I can do is subtract 1, that'll give me 9, or I could subtract 4, giving me 6, and finally I can subtract 9, giving me 1. Notice that there are no other perfect squares to try. The next perfect square would be 16, but that would be too large for my 10, so I don't need to go over it over here. Let's say I now wanted to expand this 9 node. I would get children like this, again branching for every perfect square that I can take out of that quantity, and so on and so forth. If we look at the right-hand side of my tree, I actually just discovered a way to create my input of 10. In other words, I can look at this path. Since this path terminates in a 0, that must mean that we have just found a way to sum up perfect squares such that we get 10. If I look at the numbers along this path, I'm really saying 9 plus 1. So let's expand this 5 node, as well as this 2 node, and we'll build the full tree for the subtree rooted in 6. That would look something like this. And so you can probably foresee that this tree grows very quickly. And so we're going to avoid drawing the left-hand side of the tree, although now we know the core pattern that we can use to generate it. So if I look at this subtree, I have a few different paths that terminate at 0, right? I can look at this path, which represents another way I can create my input of 10, but I should obviously prefer a shorter path, right? If I count the number of edges within a path, that would tell me the number of perfect squares I use to accumulate that sum. And obviously the shortest path we should return here is 2, because we're using a 9 and a 1. But let's go through how we can actually code this one up. So as always, if I have this visualized as a tree, then I should be able to frame it as some recursion. So in my base case, if my input is 0, then what I should do is return 0. 0 is a great return value because what we're saying is to create 0, you need to sum up 0 different perfect squares. So I'm going to plug in that return value for all these leaf nodes. And as I return these values to their parents, what I have to do is add 1 to them always. That way I can start counting the number of edges. So if I look at the very bottom right now, the 0 returns, then I add 1 to it, then it returns upward, add 1 to it, and 1 more time to get over here. Notice that I have a 3 over the 3 node, which means that I need 3 perfect squares to create 3, which makes sense because you have to do 1 plus 1 plus 1. Let's say we return at this 4 node. Since this node's receiving 2 different values, what it should do is choose the smaller between the 2, right? Because this problem's asking us for the least number of perfect squares, so I need to minimize here. So I should prefer the 0. What I should also do is add 1 to it to count the edge. And so what I'm saying right now is there must be only 1 perfect square that I need to get a quantity of 4, which makes sense because 4 itself is a perfect square. So I should be able to notice any correctness even as I evaluate these subtrees. So we'll take some time to evaluate this further. Till finally at the 6th node we get a result of 3. And this 3 represents a few different paths we can take that are of minimal length. So I think by now you understand the logic we need to evaluate this tree. This tree is going to be a little large, so I won't step through the full example. We can already foresee the complexity of this though, right? Whenever I have a tree structure like this, I'm describing all the different recursive calls that I make. So if I'm able to figure out the number of nodes in this tree, that would tell me the time complexity that stems from the recursion. What I know is the height of this tree is definitely going to be n, right? Because the longest path from the root to a 0 would be just by taking a -1 again and again, right? So the height of this tree is going to be n. When it comes to the branching factor, it's actually dynamic. So given a node, we know that we branch for every perfect square that we can fit inside of it. We know that given a node n, there would be square root of n different perfect squares. So that'll tell us our total complexity. We'll say that the time complexity is going to be the square root of n raised to the nth power. Like usual, the branching factor of our tree is going to be the base of that exponent. In this problem, the base is no longer 2, right? We were dealing with a lot of problems where we just have a base of 2. Now we have a branching factor that's based on the square root of that number. So that's why we say we have square root of n raised to the nth power. The exponent of n, of course, represents the number of levels in this tree or the height of the tree. In a similar way, the space complexity is just linear, O of n, because of the height of our tree. We know that we're going to need, at most, n stack frames in our deepest call stack. And like you could probably guess, this is actually going to be framed as a dynamic programming problem, right? What we can do is notice some overlapping subproblems looking at our tree. You can capture a few. I'll just point out this duplicate 5 node. And of course, as we grew our input larger and larger, you would have more and more overlap. So if you do things properly here and you implement memoization to capture the dynamic programming nature of this problem, what you should be able to do is bring it to some sort of a multilinear function. Overall, your time complexity would be n times the square root of n. And your space complexity would still be O of n. I'm sure you're wondering exactly how we implement this one, so maybe what you want to do is try to code it up on your own. If you get stuck, you can find me in the code walkthrough. I'll see you there. Hey programmers, Alvin here. Right now let's go over the Python solution for the summing squares problem. So like we said in the approach video, we'll start by attacking this one recursively, and then we'll optimize it in the long run with our classic memoization, right? Because this is indeed a dynamic programming problem. And so initially we're given some number n as input. So I know over time through my recursion, I need to make that number n smaller and smaller, right? So I'll start by checking if n is some small number. We have some options here. I think the best way to capture the base case would be to check if n is equal to 0. In other words, how many perfect squares would you need to add up to 0? Well, the answer is 0, right? You would need no perfect squares. So that'll serve as a nice base case here. Now I'm really going to lean heavily on what we drew out in the approach video. So I need to branch for every perfect square that I can take out of n. So what I'll do is iterate through some possibilities. So I'll say for I in range, and I'll start at 1. And I do want to iterate up through all of these squares that I can take out of n. For now, I'll put n, but we'll have to readjust that to make sure we don't go negative, right? I don't want to subtract too large of a number from n. But I know what I need is a pattern like this. I'm going to generate a square by taking I and multiplying it by itself. So on the first iteration of this loop, square is going to be 1. On the second iteration of this loop, square is going to be 4, right? Because I'm doing 2 times 2, which is 4. And I want the last iteration of this loop to give me really the square root of n. So what I'll say is iterate up to math.square root. So I need to import the math module here. So I'll say import math, lowercase math that is. And then I'll check math.square root. So take the square root of n. And I have to watch out here in a Python, sometimes math.square will give you a decimal number, right? So what I want to do is also round that down. So I'll say math.floor, round that quantity down. And the second argument into range is exclusive. So I will also want to possibly maybe increase this by 1. Nice. So on the last iteration of this loop, I is going to be the square root of n, which means square is going to be equal to n, which would be perfect here. This is just how I'm going to iterate through all of the possible squares I can subtract from n. Nice. And so at this point, let me go ahead and perform that subtraction. So I'll do n minus the square. And what I want to do is take that remaining quantity and call summing squares on it. And so I know that this call is going to give me back a number, right? It's going to tell me the minimum number of squares required to generate this remaining quantity, right? If I had to sum them all together, all those squares. And what I want to do is start some min value logic. So I know I'm going to need to minimize here. So I'm going to create an outer variable. I'll call it the min squares. I'm going to set that to infinity. Because if I want min value logic, using a very large number as my default is the way to go. Now over to my recursive call, if this is going to give me back the number of squares required to make the remaining quantity, the number of squares required to make the entire quantity n would be 1 plus that, right? Because I have to count the single square I just subtracted right now. So that'll give me my good counting logic, and I'll call that my num squares. And now I want to take the minimum of all of these num squares, because remember, I'm iterating through all of my possibilities of what I could subtract. And so at this point, I can do min squares equals, I'll use a built-in min function in Python. You can also use a conditional if you wanted to. I'll pass along the num squares and the current value of min squares, and this would update min squares if num squares is smaller. So that'll be good to go. And then finally, I can return min squares. All right, so this looks like a brute force solution. Let's give it a test run for now. See what we get. We should just time out. I do want to pass at least the first few. There we have it. And yeah, there we start to time out as things get modestly large toward the latter test cases. And so let's work in our memoization strategy. So I'm going to split this up into a helper function. So this recursive function will be underscore summing squares. Then I'll build my main function up top. That way my main function can pass along a nice memo dictionary. By now you understand this formula, right? I'm going to return whatever that recursive function returns. And I do want to pass in a dictionary inline here. And then in my recursive function, I can accept that memo dictionary. And I only have a single argument that changes to this function, so I could just use n as my key, right? The keys of my memo are going to be numbers n, and the corresponding values are going to represent the minimum number of squares that can add up to that n, right? So if I've seen this n before, so if n is in the memo, then I would have stored its value inside. So return memo at n. Now what I want to do is make sure I pass along my memo into my recursive call over here. And then I just go straight to my return line in the recursive case, so over here, and whatever I was about to return, store it in the memo first using your key of n. right? And then return that same value. That way you can still perform the recursion over here, right? Because I'm assuming that this function returns a number so I can add stuff to it. Like I always say, be sure to use your plain argument as a key for your memo. So I'm not trying to key inside my memo using n minus square, right? I simply use n and you'll be good to go. So let's go ahead and run this now. Awesome, and there's a solution for this summing squares problem. Hey programmers, Alvin here. Right now let's go over the approach for this counting change problem. So in this problem we're going to be given two arguments. We're going to be given a target amount as well as an array filled with some coin values. And what we want to do in this problem is return the number of ways that it's possible to make the amount given the coins in the array. And we can reuse a coin value as many times as we want. And so for this particular example, let's go through the ways we can make an amount of 4. One way would be to use just a bunch of 1-cent coins, or you could do a 3 plus a 1. You can also do a 2 plus a 2. And finally, you can use 1 2-cent coin and then 2 1-cent coins. And so that means there are 4 distinct ways to generate our amount. So let's trace through an algorithm we can use to solve this one. We'll start by structuring the different decisions we can make when it comes to building our amount of 4. So I'm going to use 4 at the root. And like we're used to, let's go ahead and branch for every coin value that we have available. In other words, what I could do is take a 1-cent coin, in which case I reduce my target amount from 4 to 3. Or I could take a 2-cent coin, in which case I have 2 cents remaining. Or I could take a 3-cent coin, in which case I have 1 cent remaining. Now you've seen this pattern a few times in the course already. If we built out the full tree, we'd end up with a structure like this. Notice that we terminate wherever we have 0, because that must mean we actually successfully built our target amount. We know that a 0 leaf would represent one of the ways to create our amount. Looks like we have too many zeros here. You're going to see that we have 7 zeros, but we said that there are only 4 ways to create our target amount. Let's start by interpreting one of these paths. So let's say I looked at this path. This path would represent me taking coins 1 plus 2 plus 1. And if I look at another path like this one in pink, this would represent the way of taking 2 plus 1 plus 1. If you look at those two paths, they actually represent the same coins, right? I'm using a single 2-cent coin and then 2 1-cent coins. I just took them in a different order. And that's why we have a high count right now. We're actually counting duplicate ways. And so I don't want to return 7, although my tree says that. I should really return 4. So actually structuring our tree like this is not going to be the way to solve this problem. So what would be a better way? Well, we can still use our tree structure, so we're going to break this one down recursively, but we want to build it in a way where we don't have any duplicate paths, right? And so what we'll do is, starting at the root of our tree, we're going to make a decision for just a single type of coin. So at this top level of my tree, I'm only writing a decision for my 1-cent coins. And so for this coin with a value of 1, what I'm deciding on is how much of this coin to take. So I could take 0 1-cent coins, in which case my quantity that I'm targeting, my target amount, still stays at 4. Or I could take a single 1-cent coin, in which case my amount is now 3. If I take 2 1-cent coins, then now my amount is 2. And this would just carry further until I've exhausted all the possibilities for my differing quantities of 1-cent coins. So notice here along the edges of my tree, now I'm denoting the quantity of the coin I'm taking. And at this first level, I'm taking coin 1. What I can notice immediately is I already have a node that terminates at 0. So this must mean that represents one way I can generate my amount of 4. And what this path represents is really me taking 4 1-cent coins. And on the next level of the tree, what we'll want to do is make the same decisions, but for our 2-cent coins. So let's say I wanted to expand this node of 4. What I do is branch for different quantities for my coin value 2. So I can take 0 2-cent coins, 1 2-cent coins, or 2 2-cent coins. And that would give me 4, 2, and 0 as my remaining amount, respectively. So we're going to need some more room here. Our tree's getting a little wide. What I can do is notice this amount of 1. Since I'm trying to decide how many 2-cent coins to take, I actually can't take any 2-cent coins out of that amount. So this darkened node basically is going to be a dead end. So we can effectively ignore it. That's going to be true throughout this tree. Whenever we have an amount that we can no longer shrink, we actually don't need to expand that node anymore. And so let's reorganize things over here. Now let's expand this node of 3. And again, I'm branching for differing quantities of 2-cent coins, right? So I can take a 0 2-cent coin, or I can take just 1 2-cent coin, in which case I result in an amount of 3 and an amount of 1. We'll carry this further for the other nodes at this level. Notice at this point, we've just encountered more 0 amounts, which means they represent other ways to create our target. So far we've counted 3 distinct ways to create our initial target amount of 4. Finally, at the bottom level, we choose different quantities for our coin value of 3. Notice that some of the leaves here don't terminate in a 0, which means that they don't represent valid ways to make my initial amount. What I can notice at the bottom level, though, is I have an additional 0. This would actually give me all of the 4 different ways I can create my target amount. So the key pattern here is we want to make sure that up front we choose different quantities for a single coin value before moving to the next coin value altogether. What I don't want to do is flip back and forth between different coin values, because then I would end up looking at duplicate ways. If you think about how we have the tree structured now, we have a very short tree, right? This tree's height is just going to be the length of the coins array, because at every level of this tree, I'm choosing for a different coin value. So although my tree is very short, I actually have now a very wide tree, because now I'm iterating through differing quantities. It's like you can probably foresee, we can totally structure this problem like a dynamic programming problem, meaning you could spot duplicate subtrees here. Let's take into account the shape of our tree to come up with the complexity of this. So if we implement this wisely with some dynamic programming via some memoization, we should end up with a time complexity that's a multilinear. So just A times C, and a space complexity that's also A times C. We say that the time complexity is A times C because A is the width of the tree, and C is now the height of the tree. And in general, the number of nodes would be the height times the width. The space complexity is also going to be A times C because of the different keys we're going to need to put inside of our memo hash map. You're probably wondering exactly how we implement this and why the complexity is the way it is. And to do that, we're going to actually have to implement the code together. So at this point, you'll want to join me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now, let's go over the Python solution for this counting change problem. So as always, do make sure you watch the approach video first. Because like we said in that approach video, we're going to tackle this one recursively. And we'll start with a nice base case. We're going to check, all right, if our amount is equal to 0, right? So if my amount was equal to 0, in how many different ways can I make 0 cents? Well, there's only one way to do that. Just do nothing, right? So just return 1 as my base case. And so like we said in the approach video, the key for this one is during your recursion, you want to choose different quantities for your same coin. Right? If I make all my choices up front for the same coin before switching to a new coin altogether, I won't have any duplicate ways counted. And so I want to make this my recursive function. So that'll be my recursive helper. I'll rename it to underscore counting change. And then for my main function, what I wanted to do is invoke my helper function. So I'll call it over here. And it's also going to not only pass the amount in coins, but an index starting at 0. I can take in that index over here. And so this index represents the current coin I'm choosing for. So what I'll do is index the coins array at I, and that'll give me a single coin value. So for example, let's say we were stepping through example 0, 0. Let's say my index was 1. That would mean I'm looking at coin value 2, right? This one over here. What I want to do is choose different quantities of this coin to take those out of the amount. So what I'll do is iterate over here. I'm going to use a loop, and I'll say for quantity in range. And as I iterate through quantities, what you want to be sure you do is give yourself the opportunity to take none of this coin. So you want to start at 0. You want to go up to the last valid kind of quantity you can take from your amount. So I'm going to need to do some math here. Let's say I took my amount and I divided it by my coin. So let's think about the math here. Let's say that my amount was 20 and my current coin was just a 5. And what I'll do is 20 divided by 5, so this gives me 4, which means I can take at most 4 5-cent coins right now. So that'll be good to go. But what I want to be aware of here is for the range function in Python, the second argument I pass is going to be exclusive. If I want to include it, I'm going to have to increase it by 1. So I'll add 1 over here. Now let's think about a scenario where the math doesn't work out perfectly. So let's say that now my amount was 22, right? If I do 22 divided by 5, I get 4 point something, right? And that really means I should take at most 4 out of this quantity. So what I want to do is actually round this division down. A quick way I can do that in Python is to do //. That will actually just drop the decimal part of the number. So that'll be good to go. So I'm iterating through all of these quantities, and now what I can do is I can multiply the quantity by that coin, and I can subtract that from my amount. I'll put parentheses here to be more clear. That's going to give me my remaining amount that I need to call recursively on. So I'm going to call counting change on that remainder. I'll pass along the same coins, but I should increment my index, right? I just made a decision for the coin at index I. Now in my next call, I need to make a decision for my coin at index I plus 1. Nice. If I do my recursive leap of faith here, I know that this is going to give me back a number, representing the number of different ways that I can make the remainder. I want to count the total number of ways, so I need to accumulate a sum here, just like we saw in the approach video. So I'll create a variable called total here. We'll say total ways, start at 0. And as I return from these calls over here, I'm going to get back a count. I'll add that count into my total ways, like so. Then after I'm done iterating through all of those possible quantities for this coin and add them all up, I'll just want to return the total ways. That should be our core algorithm here. So the key insight is we're iterating and branching for different quantities of a single coin. We just apply that again and again. So let's test this code. And so it looks like we're getting an error. We're saying list index out of range, and that would be for the coin array, right? And so we'll probably want to cache this with an additional base case here. So let's say we just finished the last coin. So let's say we had the case where our coin index is equal to the length of coins. So if we do a quick check here, let's say that my coin's length is 3. I know the last valid index is 2. So if it's a case that my index is 3, then I'm out of bounds. What I can do is just, I think, return 0, right? And so in that case, let's try that. Because I don't want this to interfere with my counting. So if I return 0, it's not going to contribute anything to my total ways. Let's try that now and see what we get. Good, so we're passing a few. And we're starting to time out. That's because we have an exponential runtime right now. So like we always say, we'll memoize this dynamic programming problem. So we're going to pass in a memo dictionary. Take it in over here. And I have to recognize what arguments change to my function here. So the amount changes as well as the index. And so I need to be sure to use both of those pieces of information as the keys of my memo. What we're always doing with memoization is we're taking the arguments that dictate the output or the return for a function, and we're making it the keys of the memo. And so what I can do is create a key, and I'll make it just a tuple of the amount in coin, or the amount in my index rather. And from there I can write some classic memoization code, right? If the key is in the memo, then return the stored value. And then where I do my recursion, I pass that memo to be shared by everyone. And then I need to be sure to locate the return for my recursive code. So over here, store that value in my memo before leaving. So memo at key equals that. And then just complete the return like before. So return total ways. So let's run that now. We should be able to bring our complexity down to a multilinear, right? It should just now be A times C, where A is the amount and C is my number of coins. Hey programmers, Alvin here. Right now let's go over the approach for this array stepper problem. So in this problem, we're going to be given an array filled with some numbers. And what we want to do is situate ourselves at the start of this array, so the first index, and our goal is to travel to the very last index of the array. And the rules of this game are, based on the value in our current position, that would tell us the maximum number of steps we can move to the right. So for example, since right now my current value is 2, at most I can move 2 positions to the right. So let's say I took 2 steps to this next 2 over here. From this position I can take at most 2 more steps, so I would land at one of these zeros. Since I have a 0 in my next position, that would actually mean that that would be a dead end, because I can't travel to the endpoint using a 0. And so let's actually rewind this. Let's say we were back at our starting position. Since our current element is 2, I can move at most 2 positions, but that also means you can move just 1 position to the right. So the correct move would be to take 1 step to the right, landing at this 4. Since my current element is 4, I can take up to 4 steps to the right, meaning if I took exactly 4 steps, I would end up at my goal position. So it would actually win the game over here. And so this would be an example of an input where we return true, meaning that it is possible to travel from the beginning of the array all the way to the end. If there's no such path to travel from the beginning to the end, then I would return false. So let's step through this example visually. What we'll want to do is label all of the indices of our array. And we know that we begin at index 0 of the array. So I want to draw a tree to sketch out all of the choices and options I can take as I travel through my grid. And inside of the nodes, I'm going to designate my current position. So I start at index 0. So I'm at index 0, and that means that my current element is 2. So I can move up to 2 positions to the right, meaning I'll land at either a 1 position or a 2 position. Let's say I landed at the 2 position. From here, I can take 2 more steps. That would bring me to the 3 and 4 positions, respectively. And I know that these 3 and 4 positions are going to be end nodes, so I should not expand them. Let's say I expanded this 1 to the left over here. Since the element at this position is a 4, referencing the array in the top left, I would have exactly 4 children coming out of this node. And again, we can expand this child of 2, giving us 3 and 4 respectively. And that would actually be the full tree for this problem. The 3 and 4 nodes are dead ends. I can actually recognize that I was able to make it to the final index of 5, because I can see the 5 node. So whenever my current position reaches the end of the array, that should be a signal to return true. And for all of the dead end positions, they should return false. And by now we're familiar with this pattern. What I should do is have this true return all the way up my recursion tree. So let's say I was evaluating this node over here. This node's going to receive false from its left and right child, in which case it's also going to return false. And as I continue this process up the tree, whenever a node receives a single true, it is also going to return true. That way, a true value goes all the way up my tree. I get my final answer. And so to recap, the pattern here is to take some current position and look at the element stored at that position. That element would tell us how many steps to the right I need to make. And that would also tell us basically how many recursive calls I need to make. I need to make a recursive call for every next position I can occupy. If we take a look at the structure of this tree, we can notice something special about it. This is actually a dynamic programming problem. What I can do is recognize some overlapping subproblems here. In the case of my visual tree, I can notice any duplicate subtrees. There's an obvious duplicate subtree rooted in 2 over here. And I know if I had a bigger array, and depending on the elements within the array, I would have more and more overlapping subproblems. So we're definitely going to benefit from some memoization here, just like we're a fan of. So let's talk about the complexity if we optimize things over here. What we'll say is n is the length of the array, in which case the time complexity would be n squared. And the space complexity would be O of n just from the hash map we'd use as our memo, right? We know we're going to store each position as a key of our memo. But I'm sure you're wondering, why is the time complexity here so specific? Well, it really has to do about a contrived worst case scenario we should have in the array. What we have to worry about is, technically in this problem, we can change the number of recursive calls that we take, not just by manipulating the size of the array, but by also manipulating what values we put as the elements in this array. Because remember, based on the element in our current position, that tells us how many spaces ahead we should look. So if you look at this particular example I contrived, it would actually be a case where we should return false, meaning it's not possible in any way to ever reach the endpoint. Basically, whatever path you take through this array, you're always going to be one step short. So let's say I started the game here. I begin at this first position. Since my current element is 7, I can look up to 7 spaces to the right, which means I can also look just 1 space or just 2 spaces or just 3 spaces and so on to the right. In other words, since I'm currently at this position of 7, I would have to look ahead through all of these other positions. Let's say I was at position 6, I would have to look through all of these following positions. And I would do something very similar at position 5. So basically what we're saying is, for every position of the array, we have to look through all other positions of the array to the right. And that would end up giving us an n squared behavior. And don't worry, n squared is actually an acceptable time complexity for this one. What we should notice is n squared is not an exponential runtime, right? It's a polynomial runtime. We don't have a 2 to the n runtime, which would be way worse, and that would actually be the runtime of the brute force. So overall, I'm pretty satisfied with this one. All right, so what I want you to do now is try to code up this one on your own if you haven't tried it already. And if you get stuck, you can find me in the walkthrough video. I'll see you there. Hey programmers, Alvin here. Right now let's go over the Python solution for this array stepper problem. So like we said in the approach video, do make sure you watch it first. What we want to do is solve this one recursively, and we're going to give ourselves a way to track our current position. So I'm going to need to track an index here. I'll start by organizing my code into a main function as well as a recursive helper function. So my recursion will be performed by this underscore array stepper function. It's going to take in the numbers array to reference, but also some current position. I'll just call it I. And then when I call that helper function, I'm going to call array stepper over here, the underscore. I'm going to pass along 0 as my index because I must start at the first index of the array. Nice. Now we can start forming our logic. So I'm going to start with my base case. We know that in this problem, we want to return Boolean data, right? True if it's possible to reach the end, false if it's not possible. So we'll check if my index, if it's able to reach the last index of numbers. So I can check if I is equal to length of numbers minus 1. Always bear in mind some off by 1 potential here. So if I had an array of length 4, the final index would be 3. That's why I subtract 1 here. So if I hit the end, then return true, because it's definitely possible to travel through the array. And I think at this point, we can start to write the rest of our recursive logic here. So what I'll do is maybe reference the value stored at my current position. So recall, at any point in time, you're limited in how far you can move. So when my index is 0, I know that the value is going to be 2, which means I can move at most 2 spaces to the right. So I'm going to store that as a variable. I'll say a numbers at I is going to be set to be my, we'll say, max step. Now I want to iterate through some different quantities up to my max step. So I'll say for, I'll say step in range, and we want to take steps that are 1 up to and including your max step. If I want to be inclusive with my max step, then I'm going to need to increment by 1 here. That's because the second argument to the range function in Python is going to be exclusive usually. Nice. So if I want to calculate my next position, what I should do is add the step to my current position. Remember that my current position is I. So if I do I plus step, that'll give me my next position. And I want to pass that recursively into my max stepper function. So keep your numbers the same, but pass that next position. Nice. And here I do my recursive leap of faith, right? Think about what type I get back from this function. It's going to tell me Boolean, right? True or false. Is it possible to begin at this position and travel all the way to your endpoint? And if that returns true, so I'm just going to check if here, if that comes back as true, then I should also return true. Let's say it came back as false, then that's okay. I'll just go to another iteration of this for loop and check another forward step. But let's say I finish this for loop and none of these if statements were true. Then what I should do is default and return false, meaning it's not possible to travel to the endpoint using any of my available moves here. So this should be our core algorithm, it looks like. What we'll have to notice here is occasionally, especially when I do this logic, I could be looking out of bounds. So for example, let's say that my current index position was the second to last position of the list, right? Let's say its value was like 5. When I look 5 steps out of bounds or 5 steps to the right, that's going to be well outside the range of my list. So what I want to do is remedy that by fixing this base case. If you're able to hit the last position but also go beyond it, then you can return true, right? Because if you were going past the end of the array, then based in the context of this problem, that means you could have also landed exactly on the ending point. So that should be a nice base case for us. Let's go ahead and test this code, see how we're doing. And if all is well, at least for the first few examples, we can start to memoize this one together. So passing a bunch, and yeah, looks like we're timing out on a very large test case toward the end. So we'll do our memoization strategy. So I'm going to pass along my memo dictionary. And like we always say, I want to make the arguments that change in my function, in my recursive function, I want to make those the keys for my memo. So numbers doesn't change, but I does, right? I represents my current position. So I just need to use I as the key of my memo. So this is very classic code for us. So if I is in the memo, then I've seen this before. What I can just do is return the value stored for that position I. And then in my recursive code, where I make my recursive call, pass along the memo to be shared so you can use it like a cache. And then whenever you have your return statements in your recursive section, so in this code, what I want to do is store those values into my memo before returning. So that's pretty straightforward for me. What I'll do is just save memo at key, or memo at I rather, make that equal to true. Likewise, memo at I over here equal to false. Some pretty standard steps to our memoization recipe. So with that change, let's give it a run now. Before I actually run, I want to make sure I pass in a dictionary here as the memo. Let's try that. And we should be able to pass that last example now. Awesome, and there we have a solution for this array stepper problem. All right, programmers, what we want you to do is practice this problem because we're going to make it a little more interesting in the next few problems, increasing the difficulty. I'll see you there. Hey programmers, Alvin here. Right now let's go over the approach for this max palin subsequence problem. So in this problem what we want to do is take in a string and return the longest subsequence of this string that is also a palindrome. And so what a subsequence is in the context of this problem is some string I can obtain by deleting some characters of our original string. So for example, what would be the answer for this particular input? Well, I can delete any characters within this string, but I have to keep the relative order of characters the same. So let's say I deleted the x. That would give me LUUL, which is indeed a palindrome. Recall that a palindrome is just a string that's the same forwards and backwards, and this would actually be the longest palindrome I can form as a subsequence. Since this length is 4, I would want to return 4 as my final answer. So in short, what we want to do is return the length of the longest palindrome we can make that's also a subsequence. Bearing in mind that a subsequence can be generated by removing any characters we want from the original string. Let's take a look at another example here. If I was given this string, to form the longest palindrome, what I could do is delete the T and the D. Deleting those two characters would give me SOS, which has a length of 3. That would be the longest palindrome that is also a subsequence. We can take a look at a trivial example as well, and this will help us design our code. Let's say I only gave you a string with a single character inside. Well, trivially, this character is itself its own subsequence, and it's also a palindrome. We can always treat something of one length as a palindrome. And so we should return 1 in this instance. So let's come up with a strategy for this one. We'll step through the example of LXUUL. In the long run, we know that the answer we should get is 4. We know that this problem basically has us decide over which characters to delete, if any, to form a subsequence. And so what I'm going to do is draw the decision tree that I can take as I make those different options. So we'll start with our original string at the root. Now that I have the string, what I want to do is consider any palindromic characters that I can match right now. To do this simply, what I could do is just look at the first and last characters of my current string. In this particular scenario, I see I have an L at the front and an L at the rear. So what I can do is actually match these up. If I match them up, then I should actually cut them off of my next string. So I should transition here to just XUU, and the logic being that I have a match at my front and my back, so I can remove both of those characters. And I know in the long run, I want to return the length of the longest palindromic subsequence, and so I'm going to need to remember how many characters I just matched here. I matched 2 characters, so I'm going to label that number along the edge. Let's continue this pattern. Now we're at the XUU node. What I can do once again is try to consider any palindromic characters. What I should do is look at the first character of X and the last character of U. Unfortunately, they don't match, right? So I have to do different logic here. Since they don't match, what I need to do is branch. Along my left branch, what I can do is just remove the first character. So if I remove the X, I end up with UU. And I'm going to label this edge with the number 0 to indicate that we did not score any match. But I should have also branched by removing just the last character. So if I remove the last U, I would have ended up with XU. And again, I label this with 0 because I didn't perform any match. Now from here, I just apply the same algorithm recursively. Let's say we were evaluating that left node and want to expand it. If I look at the first and last characters of this string, I have U versus U. They totally match, and so I should remove both of them. I should label the edge with 2. And when I do that removal of both of my U's, I actually end up with an empty string as a leaf. And that will probably translate into a base case. Let's continue expanding the right-hand side. So for the XU, I can consider my first and last characters, so X versus U. They are a mismatch, so I need to branch twice, right? In one scenario, I remove the first character, so if I remove X, I end up with U. In the other branch, I remove the last character, giving me just X. And again, I label the edges here with 2 zeros to represent the fact that I did not score any match. I think this would be the full decision tree that we need. So somewhere hidden in this tree, we actually have the answer of 4. What we'll want to do is maybe lay out some explicit base cases here. We know that our leaves terminate in relatively small strings, and I have 2 cases here. So let's say we considered those base cases. Let's say we had a string whose length is 0. Well, then we should also return 0. And what's the reasoning behind that? Well, if I gave you an empty string and I asked you what's the longest palindromic subsequence in the empty string, well, it's going to be 0, right? Because you have no characters to consider. So I'll jot down that 0 wherever I have empty nodes in my tree. But we need another base case. Like we said at the start, if we were given a string that contains exactly 1 character, so its length is 1, then we should return 1 because that entire string is trivially its own palindromic subsequence. So for all of my nodes that contain just a single character, the base case for them is also going to be to return 1. And from this point, I can use some logic to reconstruct my higher level solutions. So let's evaluate this left-hand side. I know that the 0 is going to return to its parent. What I should also do is add the value along the edge. So there was a 2 along the edge. So I do 0 plus 2, giving me 2. If I do a quick spot check, this makes sense because I have an answer of 2 above the UU node, which tells me that, hey, the longest palindromic subsequence given UU is of length 2, right? It's the entire string itself. Let's evaluate some of this right-hand tree now. And so I know that these ones are going to return upward. And because I have zeros along the edges, I don't increase them. But now this XU node has a decision to make. What it should try to do is choose the bigger between the two values. Because I know in this problem, I'm interested in the longest palindromic subsequence. And so I want some max value logic. In this case, though, I have a tie, right? 1 versus 1. So I can just return a 1 over here. I'll carry this logic further. So I return both of these. And now I choose the larger between the two, just giving me a 2. Bear in mind in this scenario, since I have zeros along the edges, I don't increment this value. We do one more return upward. Since there was a 2 along the edge, I do 2 plus 2, giving me 4. And that would be the correct answer for this particular input. So the key pattern we're describing here is, at any point in time, we look at the first and last characters of our string. If those characters match, then we can remove both of the characters. But if they're different, then we want to do is make 2 recursive calls, one call where we remove the first character and one call where we remove the last character. If we take those 2 branches following this pattern, then eventually we'll cover every possible substring that we need to interpret. So let's go through another example to make sure we have this down pat. Let's say I had the input string of SOSD, and we know that the final output for this should be 3 because the longest palindrome subsequence would be just SOS. So we're going to start with the full string at the root. And at any point in time, I always consider the first and last characters. So I compare S to D. Since they mismatch, I need to branch twice, right? And on my left branch, I remove the first character. On my right branch, I remove the last character. And it's important that I try both of these scenarios because I'm not sure which decision will actually lead to the final answer. Let's say we're expanding the left-hand node here. So I compare O versus D. Since they're different, I have to branch twice again. And likewise for those 2 children nodes, they also form mismatches, and so I branch them both respectively. And once I get to strings of length 1 within my nodes, I know that those bottom out at the base case. So what we'll do now is evaluate that right-hand node of SOS. If I compare the first and last characters, I have a direct match. So I branch once here, and I treat the edge as a value of 2. Since I match those 2 characters, I can remove them both, resulting in just an O. Since I've hit a single character node, that would be a base case. Like we said in the last example, for any of these leaves that terminate at a single character, what I can do is treat them as a 1, right? Because trivially, if you had 1 character in your string, then that character itself is a palindrome. And at this point, we can perform all of our return logic like before. So we'll just speed it up here. For the right-hand subtree, this 1 bubbles up. We have to add 2 to it though because there was a 2 along the edge, so I get 3 here. Then at the final root, I do 1 versus 3. I choose the larger between the 2, giving me a final answer of 3. All right, so I'm feeling pretty good about this algorithm, but there's something we should notice that's important about the structure of this problem. If you chose a wise enough example, maybe a large enough example, you would be able to realize that this is a dynamic programming problem. In other words, eventually, we'll have some overlapping subproblems that we should be able to optimize away. For the last 2 examples, we weren't actually able to notice any overlapping subproblems because our examples were too small. What you're going to have to do sometimes is use a large enough example because I know, in terms of big O, I really benefit from using a dynamic programming strategy as the size of the input scales. So if I just use this simple example of A, B, D, E, F, if we carry over the algorithm, eventually we're going to see some duplicate nodes. If you look at this example, it's a good one because it signifies the worst case, right? I have no matching characters here. And like we said previously, if you have mismatching characters, then you have to branch twice. So an example like this would give me the maximal branching factor. So let's say we drew out a few levels of the tree for this. Remember that when we branch to the left, we're going to remove the first character. When we branch to the right, we're going to remove the last character. At this level of the tree, we already start to see some overlapping subproblems. I can look at these nodes of BDE, right? Since they're duplicate nodes, they're duplicate inputs, I should be able to save their results to reuse them later on. In other words, the subtrees rooted at BDE would be identical. And of course, as I made my tree larger and larger, I would have more and more overlapping subproblems. So that means we're going to use our classic memoization strategy. So if we say that S is the length of the string here, what can we say about the complexity? Well, if you take a look at what we have running in the tree right now, we would actually be considering every possible substring within each node. And so I'll say here that the time complexity is O of s squared, because given a string of length s, there are s squared possible substrings. In a similar way, we'll say that the space complexity is going to be s squared for our final solution, because we're going to have to store each of those substrings as keys of our memo. Right, so I'm looking at an s squared time and s squared space complexity, which is good because the brute force would actually be an exponential of 2 to the s. So we do benefit greatly from doing memoization here. So when we implement this in code, what we'll want to do is also be aware of any costly string operations that we want to avoid. So if you look at the diagram right now, it looks like I have substrings within each node. Creating those substrings would mean creating a copy of a string, and creating a copy of a string of length n would run in O of n time. So I actually want to figure out a way to efficiently represent different substrings of my input. So I'll just allude to this trick right now, and when we go through the full code walkthrough, I'll show you exactly how to implement this. So let's consider this tree. We know that our original input was A, B, D, E, F. What I want to do is use an alternative method for representing substrings. I know that each of these characters of my input have their own indices. Instead of putting substrings as the nodes here, what if I just represented a pair representing start and end indices? So if I constructed the same tree but using this different representation, my top level call, or my root, would look like this. Right? I have a start of 0 and an end of 4. And that means I'm considering the logical substring within that range. So this logically represents the entire string of A through F. And when I go through my left branch, I know that my left branch should be removing the first character. That should be incrementing my start index. In other words, I can have a left child of 1, 4. And that should logically represent B through F. And in my right child, I should have decremented the 4 to be a 3, but kept the start index the same. So that right child would logically represent my A through E. And if you compare these trees so far, they're representing the same information. What's great about this indexing trick is I won't have to actually create any string copies, and I know that just incrementing or decrementing some index variables is going to run in constant time. So overall, that will lead to the most efficient implementation of this strategy. All right, so what I want you to do is try to code up this algorithm on your own, and if you get stuck, you can find me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now, let's go over the Python solution for this max palin subsequence problem. So we're going to implement exactly what we spoke about in the approach video, which means we're going to solve this one recursively, as we do for most of our dynamic programming problems. Getting really good at this strategy. And so what we'll do is set up a helper function to do the recursion. So I'm going to call it underscore max palin subsequence. I'm going to give it the string. And like we said in the approach video, if you want to cut down on your complexity, avoid slicing your string. Instead, just pass some indices to represent the bounds of your string. So if I want to begin my recursion here, I want to basically look at the entire logical string. So I'm going to give it 2 indices. We'll say 0, as well as the last index, which would be length of string minus 1. And that means in our recursive helper function down here, we're going to take in 2 arguments, I as well as j. And so I is the start and j is the end. So what I want to do now is write a base case that checks if I'm looking at a string of just 1 character. I want to express that in terms of my start and end indices though. So I'm going to check, let's say if I is equal to j. That means that my start and end are pointing to the same character. Since both I and j are inclusive bounds, then that would mean I'm looking at 1 character. So just return 1. What we're saying here is if you gave me a single character, I can say that that 1 character is of course a palindrome, right? It's also a subsequence. So that'll be one base case. And I also want to check the scenario if I have the empty string, right? So that would be the case if I is bigger than j. In other words, if my 2 pointers cross, then I would be looking at a logical empty string, so return 0. Because if you have an empty string, then there is no palindrome to be found, so its length is 0. Awesome. So that looks good to go. And you will need both of these base cases, but now I can write my recursive case. And so what I'll do here is go ahead and check if I have 2 matching characters, and I want to check them at opposite ends. Since I know I is the beginning of my substring, right, and j is the end, what I want to do is check if string at I, if it's equal to string at j. Nice. And what we'll do is just do a recursive call, so max palin subsequence, do a recursive call, but move your pointers inward. So I just matched index I with index j, so I should increment I, so I'll do I plus 1 over here, and then I should decrement j. This will bring them closer together. So what effect are we having here? So let's say like the logical substring I was looking at was something like this. I would be comparing this L to this L, and if they're a match, then what I want to do is make a recursive call just looking at the inner substring now. Nice. And so if I do my recursive leap of faith, I know that this recursive call is going to give me back a number, right? Representing the length of the longest substring, that's a palindrome, within these bounds. And what I want to do is take that number and add 2 to it. The reason I add 2 is I need to count the 2 characters that I just matched myself. That would give me my total length of a palindrome, right? So what I want to do is return that value. So that'll be my case if I have a match. But it could be the case that I have a mismatch. What I want to do is try other possibilities. So here, what I need to do is make recursive calls. But on one side, I only progress I, so I do I plus 1, keep j the same. And another call, I keep I the same, and I decrement j. Right? I'm just progressing my 2 different pointers in the way I should. And by making both of these calls, what I'm doing is giving myself an opportunity to make all possible matches. Right? If I think about my recursion, I know these are going to give me back numbers, right, representing the longest palindrome subsequences within their respective bounds. And what I want to do is choose the larger between the two. We know that in any problem where you want the longest thing or the maximal thing, you need some sort of max value logic. So here's where I maximize. So between those two, choose the biggest. I can use the built-in max method in Python. I can pass in some comma separated arguments, so I'll just maybe move these guys up. And that will give me back just the number that's the biggest. And I just want to return the bigger of those numbers. Cool, so there's my nice max value logic. And I think this might be our brute force recursion. Let's go ahead and give it a test run. Not a lot of code, but some tricky logic, especially in the recursive step. So we're passing a few, and we expect a timeout. It's already starting to slow down. Yep, and we time out. So like we said, this is a dynamic programming problem. So what I want to do is memoize this. I'm going to pass in a nice dictionary to serve as my memo. And because we're using the really awesome string index trick, that way we don't have to keep slicing the string, I know that the arguments that change throughout my recursion are just I and j. So I'm going to use a pair of I and j to denote a key of my memo. Then I'll map those to their respective return values, right? So I'm going to create a key. I'll make it a tuple, because I can always put a tuple as a key of a dictionary in Python, right? Make the tuple contain I followed by j. And so if I've seen this logical substring previously, in other words, if my key's in memo, then I'll return the stored return value, right? So return memo at key. Then I'll go to my recursive calls, and there's likely 3 of them over here. And I want to pass along that memo to be shared. And like we always say, now I go to my return values in the recursion, so these statements here, and I store those values into the memo before completing the return. So for both of these, I'm just going to store them in memo at key. And I know that at any point in time, if I was executing this function, I would really either run just this code or this code, but never both. So what I can do is after this if-else statement, I think I can just return memo at key. That way I can keep my code from being too repetitive. So that's looking good. Let's give that a run once again. Awesome, and there's a solution for this max palin subsequence problem. Hey programmers, Alvin here. Right now let's go over the approach for this overlap subsequence problem. So in this problem we're going to be taking in 2 strings as input. And what we want to do is return the length of the longest overlapping subsequence that's common to both of our input strings. In this problem we're using our classic definition for what a subsequence is. So given a string, we can make a subsequence by just deleting some characters of that string. So for these 2 inputs, my answer should actually be 3 because I can overlap along this dog substring. So in this example, if I remove the s from string 1 and I remove the at from string 2, I would have dog represented here. And I want to return the length of this longest overlapping subsequence, so I should return the answer of 3. All right, so what's the intuition behind this one? Let's step through this example of cat versus AOT. And so I'll start with those 2 strings at my root. And like before, what I want to do is represent all of the different options we can take as we match up characters here, right? This is really just a spin-off of our last subsequence problem. But now that I have two strings, I have to use logic that incorporates both of them. And so what I'll decide to do for this problem is, at any point in time, given these two strings, what I want to do is look at the first character in both strings. So that means at the root right now, I consider C versus A. Since they mismatch right now, I need to do some branching. And so what I do is when I go to the left, what I'll do is remove the first character of string 1. So that results in AT versus AOT. Notice that I only shrunk string 1. Now I'm going to label this edge here as a 0 because I did not score a match. The alternative scenario would have been to just delete the first character of string 2. And I'm also going to label that with an edge of 0 because I did not score a match. So let's expand that left node. And I know that if I consider the first characters of both string 1 and string 2, I'm doing A versus A. And that would actually be a direct match. So here I only branch once, and I should remove both A's. So I'm removing the front character of both of my strings in the case of a match at the front. What I want to do is treat this edge as a worth of 1, right? I'm treating it as 1 here because I'm matching a 1 character across both of my strings. Let's say we kept expanding this left-hand side. Like we said, if we branch twice, and in our left branch we delete the first character of string 1, in the right branch we delete the first character of string 2. What we can notice in that left child is we actually have emptied out string 1. So that's going to act as a base case. So let's expand that TT node here. Because we have a match, I'm going to treat that edge as 1, and then that will result in an empty string, right? 2 empty strings we have here. Remember that if we have a match, I remove those matching characters from both of my inputs. At this point, I think we fleshed out the left-hand tree fully. Let's expand the right-hand side. And we're going to need a lot of room for this. So like before, I consider the front characters of both of my strings. So I do C versus O. I have a mismatch, so I branch respectively. For both of these nodes, they also have mismatches, and so I branch twice for either of them. At this point, we can notice something very peculiar about our tree. This is actually a dynamic programming problem, right? I can notice these overlapping subproblems by noticing duplicate nodes. So for example, in red, I have these duplicate subproblems. And even in pink, I have these duplicate subproblems. So I'll only need to evaluate those problems once, and then I can store the result in a cache, probably like a memo object, to be used later on. Now let's evaluate one of these pink nodes. It would result in these two children, and I can notice another overlapping subproblem, right? Rooted in this TT node in yellow. And at this point, we've actually denoted all of our unique subtrees or bottomed out at some base cases. So the base case I'm going to use here is if one of my strings is empty in a node, then what I should do is return 0. Because imagine if someone gave me an empty string and a string filled with some characters, and they asked me to find the longest overlap. Well, if one of your strings is empty, then the longest overlap would be 0, right? So for all of these nodes that have at least one empty string, they're going to return 0. Now let's go through how these values return up the tree recursively. So let's say I'm evaluating this left-hand side. I know this result of 0 is going to bubble up, and I should add the value I have labeled along the edge. So there was a 1 along the edge, so I add that to this return. So now it's 1. And I know that the sub-result of 1 is also going to be useful later on in the tree for that duplicate subproblem. So I'll just jot that down. Then we'll just carry over these returns, so bubbling up a little more. And now at this node, I have a decision to make, right? I'm receiving a 0 and a 1 because I want the longest overlapping subsequence. I do max value here, right? So I choose the bigger versus 0 and 1. That means I choose the 1. And this subresult of 1 is going to be useful for the duplicate node over there. So we'll just jot that down. I can carry over this result upward. And I should add the 1 that was along the edge, giving me 2 at this node over here. At this point, let's start evaluating other regions of our tree. So down over here, what we can do is return both of these values. And since I have 0 along the edges, I don't increase them, but I should choose the bigger between them. So I choose the 1 here. And I know that this one's going to be useful later on when I encounter that other pink node. So I'll just jot that down. We'll just keep doing this return. So these 1s bubble up. I have a tie here, so I'll just choose a 1. Now that we're getting the hang of this logic, we'll step through all these different returns. Once we're at the final root, I know I have a 2 versus a 1. I take the bigger between the two, so my final result is just 2, which makes sense because the subsequence that overlaps here would be the AT, right? That would be the longest subsequence that overlaps. So what do we know about the complexity of this one? Well, if we use our classic memoization strategy, then we know we're going to avoid any overlapping subproblems. That means any duplicate inputs. Let's say that n is the length of string 1 and m is the length of string 2. Think about all of the possible different nodes we can have if you had those two terms. There would be n times m different nodes. We know that our algorithm runs recursively by removing the first character of string 1 or removing the first character of string 2. Having to choose characters to remove, there would be n times m possibilities overall. If you look at the pattern within the nodes of this tree, you can also interpret this complexity as coming from the fact that we have to try all possible pairs of suffixes in either of our strings. Recall that a suffix is some substring that starts anywhere within my string, but definitely goes through the end of my string, right? So if I have n different suffixes for string 1 and m different suffixes for string 2, then all pairs of them would be just n times m. In a similar way, our space complexity is also going to be n times m because of all of the keys we need to store within our memo object, right? If I have n times m different input possibilities, then I know I need a key in my hash map for each of those. And so we'll get this multilinear n times m complexity if we implement this in the best way possible. So my tip to you is to avoid any string slicing, right? Although we visualize this by representing like substrings within every node, if you actually created these substrings during your recursion, you would actually incur a worse complexity. So don't use slicing. My advice to you is to instead track some indices, right? So can you figure out a way where you can just use some numbers to represent your different substrings, your different suffixes? If that's a little hand wavy, don't worry. We'll step through this full algorithm in the code walkthrough video. So I'll see you there. Hey programmers, Alvin here. Right now, let's go over the Python solution for this overlap subsequence problem. So hopefully you watch the approach video because this is going to be a spin-off of our last subsequence problem. So we'll start by structuring some familiar patterns. I want to avoid any slicing throughout my recursion here, so I'm going to use some indices to track my string 1 and string 2. So what I'll do is create like a helper function that does the recursion like usual. I'm going to call it underscore overlap subsequence. I'm going to pass it the plain old string 1 and string 2, and I want to pass some additional arguments initialized to 0. And then when I actually write this recursive helper function, I'll take in those arguments as I and j. So I is going to represent the logical start of string 1, and j is going to represent the logical start of string 2. Nice. So I can avoid any slicing. So let's start with our base cases here. So we know that in general for these like string problems, especially if I'm doing it recursively, I want to make my strings smaller and smaller, right? Because that would give me an easier and easier subproblem until I have a trivial subproblem. So what I'll do here is check like if I have an empty string. And to do that using this index trick, what I can do is check if my index for I is equal to the length of string 1. So if I do some quick sanity check here, let's say that string 1 had 3 characters. That means its length is 3. But if the index that I'm looking at is 3, that's already out of bounds. So that should be interpreted as like the empty string, right? In general, if I'm given an argument I, that means I'm looking at the substring that starts at index I and goes through the end of the string. Nice. Now I want to check OR, a similar statement for j in string 2. So OR j is equal to length of string 2. So what I'm expressing here is if either of my strings are empty, then what should I do? Well, I want to return the length of the largest overlapping subsequence, which would be 0, right? If one of them is empty, then you can't really have any overlap, so return 0. So that'll be a nice base case for us. Now let's start stubbing out our recursive code. So I know this problem's all about overlap or matching characters. And what I'll do is just check if the characters at indices I and j of their respective strings, if they match, then I can do a specific recursive call. So I can check if string 1 at index I, that's equal to string 2 at index j. And remember, think of like I and j as like the logical start of your substrings you're interpreting. I'm basically checking if my front characters are the same. And so if they're the same, what I should do is make a recursive call. So overlap subsequence. Since I've just matched these two characters, I want to progress both of them. So I should increment I. So I do I plus 1, and I do j plus 1. If I do a quick smell test, that looks like it makes sense because I need to make sure I increase I and j over time so they eventually hit in this base case because they start at small numbers, right? And I want them to eventually become large numbers. And that also makes sense because I've just matched up indices I and j. So I don't need to look at I and j ever again. Instead, just look at the next characters. If I do my recursion over here, I think about what type this returns. It's going to give me back a number, right? Representing the largest overlapping subsequence at these substrings that start at I+1 and J+1. Whatever number I get there, I want to add 1 to it. I'm adding 1 because I should count this match I just made. So I'm looking for like the alignment between my two strings. And I'll just return that quantity. Nice. And then in the else case, else I don't have matching characters, so I need to try progressing either of my strings. So what I'll do is I'll go ahead and make one call where I increment I but keep j the same, so just pass in j, and another one where I increment j but keep I the same, just like so. That'll give me all of the opportunities to actually match up differing characters. I know that these calls return numbers, right? I want to choose the bigger between them, so I can use the built-in max method in Python. Move this on up. So between those two options I take, choose the one that gives a bigger answer, and then just return it. That should be our baseline recursion. Looks very similar to that palindrome subsequence problem. Really just a spin-off. Now we're dealing with two strings and some adjusted logic here. So let's give this a test run, see how we're doing. Pretty tricky problem. And if this is passing some test cases, we'll actually memoize it together. So it looks like we're slowing down. Yep, and we're starting to time out. So at this point, it's pretty academic, right? Love my memoization strategy. Really just solve the brute force recursion, and then you always do the same steps to memoize it. I'm going to pass along a dictionary to be my memo object. And like you expect here, the arguments that change to my recursive function are I and j, so those should encode as my keys of the memo. So what I want to do is create that key of I and j as a tuple, and then go ahead and check, all right, if that key is in the memo, in other words, I've seen this input before, then just return the stored value, right? Because I would have put the return value inside of the memo already. And now I go to my recursive calls, be sure I pass along the memo to all of those calls, and I have 3 different calls here, so it's important that you share it all. And then for my recursive return, so over here, I store information in the memo before returning. So I take the literal return values, and I can just put them in the memo first. And then I'll just return memo at key. So I can still return logical information. Right, it's important that I still return because, of course, if this function is recursive, you need numbers to come back for these calls. They must be returned. So let's give that a test run. Nothing fancy with the memoization. Awesome, and this is our final solution for this overlap subsequence problem. Hey programmers, Alvin here. Right now let's go over the approach for this concat problem. So in this problem, what we want to do is take in a string as input. We're also going to accept an array containing some words. What we want to do is return a Boolean indicating whether or not we can concatenate words of the array to create our target string. So for example, for this particular input, let's say our input string was 1 is none, and we had words of is, 1, and n. We can concatenate words together from our word bank like this to form our target string. Notice that we're totally allowed to use the elements of the word bank as many times as we want. In the long run, we want to return true for this problem, right? Let's take a look at another example. So let's say our target string was smashing fashion, and our array of words was this. This would actually be an impossible scenario. The best we can do is create smash by doing sm plus ash, but then we'd hit a dead end because I need ing, but I only have ion. And so since it's impossible to concatenate words of the word bank together such that we create the target string, this is a case where we should return false. So let's come up with an approach for this one. We'll step through an example where we want to build the string food is good, and we'll use these elements as our words of our word bank. What I want to do is try every possibility for what I can use to build my target string. And I know I'm going to solve this one recursively to explore those options, so in the long run I should be making my target string smaller and smaller recursively. So what I'll do is start to visualize this like a tree, like we always do. And we'll start with the original string in our root. And what I want to do is figure out what words I can use to build food is good. What I can do is look for potential matches at the start of my string. In other words, I'm going to check if any of the words of my word bank match a prefix of my string. So what I can do is notice that I have an F at the start, and a literal word in my word bank is exactly an F. So what I'll do is remove that F, giving me the remainder of ood is good. And to be extra clear in this diagram, I'll label the F along the edge. So the logic here was we look for a word of the word bank that matches at the start of our string. And if it does, then we can remove that starting string from our next word and then just label it along the edge. There'd be another possible match here though. What I could also do is match foo, because foo is a word of my word bank as well. In which case I would do a similar transition, right? If I used foo along the edge, I would remove it from my string, giving me disgood as the remaining string. And we'll just keep applying this logic recursively. So let's try to expand this node on the right. This would actually be a dead end, right? What I always want to do is check if any words match at the start of my string. Right now my string starts with a D, and I won't be able to match any of my words. So instead, let's branch out on the left-hand side. So I have ood is good. What I can do is match the OOD. Now it gives me a remainder of is good. And then from there, I can match is, giving me with good. Then I can take a G for good, giving me just OOD as a remainder. And finally, OOD is actually a word in our word bank, so we can take that as a final word here. And that will result in an empty node or an empty string for us. So if we look in our tree, we've actually discovered one way we can create our original target string by concatenating words of our word bank. I can just look at this path that terminates in an empty string. If I look at the words labeled along the edges of this path, they're exactly the words that make up my answer. So it's clear from this illustration that we're able to build the target string food is good. But how can we actually describe this in a more programmatic way? What we'll do is understand that this tree describes some recursion, right? It's a recursion tree. So what I'll do is think of a base case that I can use and how I can use small sub-solutions to build up higher level solutions. So let's start with the base case here. We're in some familiar territory. We know that over time we're going to be shrinking our current string. Notice how the strings in the nodes get smaller and smaller as I move down my tree. What I want to do is write a base case about the smallest string, and that would be the empty string. In other words, if your string had a length of 0, then you should return true. So what's the logic behind that base case? Well, if someone asked me to build the empty string using some words, that would always be possible because I can just concatenate no words together to create the empty string. And so what I'll do is jot down this true return value wherever I have that empty node, right? Empty node represents the empty string over here. And what we'll do is just keep returning this on up. So just some classic return logic recursively. And what we'll want to do now is consider what this right-hand node should return. Remember that this was a dead end. Because we can't break down this string anymore, it's really a string that should return false. And now that these true and false values return to the top level root, what I'll just do is ultimately return true because I at least have one true, right? So the combination logic we need at every call or every node is, if one of my recursive calls comes back as true, then I will ultimately return true. On the flip side, if none of my recursive calls come back as true, then I'll just default to false. All right, so I feel pretty good about our overall approach, but let's think about the complexity of this. And for this one, we'll want to think about the worst case scenario, right? Sometimes to analyze the complexity, we'll have to think about a very contrived scenario that gives us the largest type of behavior. So here's an example I came up with. Here's a string that contains a bunch of Qs at the start and also terminates in an X, right? If I look at the words of the word bank, I just have different numbers of Qs, right? In the long run, you know that this input should return false because I can never generate that final X. But why is this the worst case scenario? Well, let's say we start to build the tree for this one. We start with our original string at the root. And what I have to do is branch for every matching prefix of this string. So I can use a Q, in which case I just reduce by one Q in my next node, or I can take 2 Qs out, or 3 Qs, or 4 Qs, and even 5 Qs. And that would give me a lot of branching, right? And at this point, I would apply the same logic recursively. If I wanted to expand that left-hand node, it would also have 5 branches. And all of these nodes would do something very similar. They would branch as many times as possible. And so the worst case scenario here is going to be when the words have a lot of matching prefixes of our target string. Right? If you think about the long-term behavior of this sort of tree, we know that the height of this tree is going to be based on the original string, right? Because in the worst case, I could just repeatedly take off a single Q again and again until I hit the empty string. But if I think about like the width of the tree or the branching factor, what I'm saying here is basically for every node, in the worst case, it's going to have 5 children. And each of those children are going to have their own 5 children. So in the worst case, from one level of this tree to the next, I would be multiplying the number of nodes at that level by 5 because I have 5 words in my word bank. So let's formalize the complexity for this one. Right now, we're describing our brute force recursion, right? If we say that S is the length of our string and N is the number of words, then the time complexity of this is going to be exponential, right? Whenever we have a tree structure like this, we can always think about the branching factor, in this case N, and keep that as the base of the exponent. And then the height of the tree, or S, would be the exponent itself. So our time complexity is exponential, which is not going to be fast enough for us, but the space complexity stays at O of S. Like usual, because we're doing this recursively, we're going to need at least S stack frames on our call stack to actually explore this tree. So you're probably wondering, can we do better? And the answer is yes, because this can be a dynamic programming problem. To discover whether or not a problem is a good fit for dynamic programming, what you'll have to do is sometimes use your imagination to figure out if you can come up with an example that has overlapping subproblems. So one example I came up with was this, right? Let's say my target was would you, could you, and my words were these. Something you can recognize is it's definitely going to be possible to create my target string. If you look at the words I chose here, I have two separate words like would and you. And I also have a single word of the entire would you. And that'll be an easy way to create duplicate nodes. So if we broke down this problem in our standard way, we start with our original string at the root, and I branch for every matching prefix. So I must look for matches at the very start of my string. One match would be using would, in which case you're left with just you, could you. And then on the right-hand side, we could have branched using would you, in which case your remainder is just could you. And if I expanded the left-hand side, at that point I can match you at the start of that string, and that would result in could you. And without building the rest of this tree, I already have some overlap, right? These two nodes are duplicate. If I have duplicate nodes, that means I have duplicate subproblems, and I should avoid recalculating them fully as I do my recursion. So I feel pretty strongly that we can use memoization to speed this up. If we use memoization, it would now be the case that our runtime would be n times s. So this is no longer exponential. Now I'm just multiplying these terms, forming a multilinear, which is pretty fast. Our space complexity stays the same. It's going to be O of s. Because we know that every node of our tree would have to be stored as like a key of our memo hash map, there will only be s unique strings that we can actually store as keys. So that's why our space complexity stays the same. Alright, so that's all I got for this approach video. What I want you to do is try to code this one up on your own. If you get stuck, you can find me in the walkthrough video. I'll see you there. Hey programmers, Alvin here. Right now let's go over the Python solution for this concat problem. So hopefully you watched the approach video first, because like we said there, we're going to solve this one initially with some brute force recursion. And then we can do some memoization to give it a passing time. And so what we'll do is start with a base case here. I know in this problem, given a string as input, and through my recursion, I want to make that string smaller and smaller. I'm going to have a base case about the empty string, right? So if s is the empty string, then what should I return? Remember the return type for your function, right? It's going to return Boolean, so I have to think about which Boolean is appropriate here. This should be a case where I return true, because I can always create the empty string by simply concatenating together 0 words of my word bank. So the empty string is trivially true. Then from there, I need my recursive case to make this s smaller and smaller. And I can only do that by matching some prefixes from my word bank, right? So what I'll do is, let's iterate through every word. So for word in words. And what I want to do is really only choose the words that I can match as a prefix of s. It's a nice built-in function you can use in Python. What I can say is, if s.starts with, check if it starts with my choice of word. So if you're unfamiliar with this method, it's a string method in Python, and it tells me true or false, does some word begin at the front of s. So that'll be good to go. Basically just checking if word is a prefix of s. And so if it's a prefix, what I want to do is actually figure out the next word to pass to concat, right? What should I do in my recursive case? And so what I want to do is make sure I chop off the prefix I just matched. To do that, I can do a Python slice. So I'm going to slice s. I have to think about the index that I want to start slicing. The move here is to start slicing at the length of the word you just took. And that would give you your suffix. Nice. So let's think about what we're saying here. Let's take a closer look at that pattern. Let's say we were analyzing maybe this first test case, right? So let's say we're at the top level call over here. So s is the string, 1 is none, and then our current word, we'll say that we're iterating through, is just 1, right? So I know that this method call is going to return true because 1 is none does indeed start with the string, or substring 1. And what I do here is I start slicing at beginning at the length of the word. Right now the length of my word is 3, so if I count those indices, I start at index 0, 1, 2, 3. So I start grabbing characters at this I, and I go through the rest of the string, so my suffix ends up being is none, which is perfect because that gives me a smaller string that I can pass recursively into my function. So that's the idea behind this slice pattern. And so what I want to do now is make my recursive call, so call concat, and check if we can make that suffix now recursively. And I can pass along the same words array, right? I can reuse words as many times as I want, so no need to modify your words here. So now I do my recursive leap of faith, right? I think about what type I expect back from this recursive call. It should always tell me Boolean, right? In this scenario, it should tell me true or false, can I build the suffix? And so let's say it was possible to build the suffix. So if that call comes back as true, I'll just be explicit here. What should I do? Well, then I should also return true, right? If it's possible to build my suffix, then it's also possible to build the full string s, right? Because to reach the suffix, I literally used a word of my word bank. So that'll be a nice pattern for us. And if it's the case that this recursive call comes back as false, well, that's okay. What we want to do is just attempt the next word in the words array. And after we try every single word, if all of them fail, then we'll return false. So that's a very common pattern for us, right? An early return and a late return over here. That should actually be our brute force for this problem. Let's go ahead and give this a shot. We expect to fail on the latter test cases because this is going to have an obvious exponential runtime. And it looks like, yep, we're timing out. So like we always say, let's use our memoization strategy. I know I need to pass in a dictionary as my memo, so I'll maybe make this one my recursive helper function using my kind of canonical underscore notation here for my helper function. Then for my main function, of course, I need to call it can concat for the test cases. What I can do is just delegate to my helper. So I'm going to call my helper function can concat. And I can give it some nice initial argument with an empty dictionary. Now I can accept that as an arg over here as my memo. Nice. If I think about the arguments that change during my recursion, it's really just s. So those are going to be used as the keys of my memo, right? I'm trying to map meaningful arguments to their return values. And so what I'll do is check if s is in the memo. In other words, if I've seen this input before, if I've solved this subproblem previously, then I can return the stored result. So return memo at s. And always be sure you pass along your memo to all of your recursion. That way it's shared like globally in the recursion tree. And then wherever I have my recursive return lines, so here 2 lines, the hard and fast way to fix this is to just put both of those values in the memo before returning them. So I can say memo at s equals those things, then still complete the original return logic. As always, we need to be sure to return data because I assume I get back data in these recursive calls. Nice. So let's give this a test run now. We should be able to bring down the complexity from an exponential to a multilinear, which is a pretty snappy solution.
All right, programmers, Alvin from the future here with a little addition. So we just went ahead and solved this can concat problem in Python. I do want to show you an additional optimization you can make, and it's actually one that you've seen previously in this module. So you will notice that here we do the slice operation, right? Here we get the suffix or the remainder of our string, and we go ahead and pass that on into our recursive call here. That's how we're able to shrink the problem size. You should be able to note that doing the slice operation like this would run in linear time. So let's go ahead and work on this code a little more so we can get rid of this linear operation. And so, like you've seen previously in this module, what you could do is use an index to kind of track where you're positioned at inside of the string. So I'm going to add an additional argument here. I'll call it I, but I'm going to initially pass it into 0, so the number argument will be over here, like so. So my top level call, I'm passing in my string and my words. My initial index is 0, also my memo is just an empty dictionary. And instead of actually manipulating the string, I'm going to just manipulate this index variable. So I is going to denote which part of the string I'm currently looking at. So for example, if I is a number like 4, that means I'm looking at the string starting at index 4 going through the end. So now I want to adjust all of my logic for this. So because the string is no longer going to be sliced, it's not going to be useful as the key in my memo. Instead, the index I is going to change. So go ahead and start rewriting these. I would use the index I for my memo key. Then over here, I need to do some work, right? I can't check if my original string is going to be empty. Instead, I need to write that logically using the index. So if I was looking at the empty string, then I would be equal to the length of s. In other words, I would already be pointing outside of the string here, right? This is already out of bounds. Great. Now I need to rewrite any other lines. For example, this starts with call over here. The nice thing about the Python starts with string method is it does take in some optional arguments. So by itself, this would be checking if the original string just starts with this given word, but you can also choose which index to look around. So I'm going to start looking at index I. So now it's going to see if your string starts with the word beginning at index I, which makes sense because I is going to represent the part of the string I should currently be looking at. And I definitely want to optimize this suffix grabbing, right? I don't want to do the slice here. Instead, I want to manipulate the index. So I'm going to drop this. I'm not going to pass along a suffix. I'm always going to pass along the same exact string. It's not going to change, but I need to work on how I change this I variable, right? So this is the current position I'm looking at. Because you're taking this word right now, we need to increase this by the length of that word. So I plus length of word. This has the effect of looking further along in the string, right? I'm able to accomplish the same logic, except now I don't have to do that slice operation. Then I'll be sure to replace all of these S's for the memo key with the index I. This is a trick that you've seen previously in the course. We're just using it in this concat problem. Originally, I didn't show it this way because I think it's a little too much to take in at once because concat is already a tricky problem. Notice that we were already able to pass some of those larger test cases. But if you wanted truly the most optimal solution, you could write it this way. Let's test it out. I think I just put the wrong order of arguments, so the index comes after the words here. So it should go like this. Let's try that again. Great, and there we have it. All right, so that wraps up our course on dynamic programming. We solved a ton of problems together. This course might be over, but the learning doesn't end here. If you want to practice more advanced DP problems, then you should check out my complete DSA course at structy.net. There I'll teach you more dynamic programming, as well as other interview topics like trees, graphs, and much more. I'll leave a link in the video description if you're interested. Thanks for watching, and I'll see you next time.